morning, everybody. So today we'll be focusing on the power of composting and carbon farming. It's a really cool, exciting topic, and we're really lucky to have Jeff Creque with us today to share his knowledge. Some of the earliest research on this was done in our own backyard on a ranch in Nicasio. And also there's a 2022 state law requiring all food waste to be composted. So the amount of food waste not thrown in the landfill will reduce the organic material in landfills by about 75% and reduce the resulting methane sent to the atmosphere. So good that we're starting to make some changes here locally. And we're going to hear a lot more about that from Jeff. So let me start sharing my screen for today's presentation. We continue our focus on earth-friendly gardening and protecting our most precious resource, soil. So elements of earth-friendly gardening, or EFG, related to soil that we've been learning about include building and protecting the living elements of the soil. We want soil, not dirt. Adding compost and mulch, protecting the soil from disturbance, compaction, and erosion, and celebrating soil's ability to sequester carbon to help mitigate climate change. We're seeing more attention being paid to this, including by our own U.S. Department of Agriculture. So I was checking it out last night, but they launched a large program in 2022 focusing on providing financial incentives to farmers involved in climate smart farming initiatives. And so actions covered by this program, including providing farmers with incentives to grow cover crops rather than leaving their soil fallow, and the purpose being to help sequester carbon. So again, I can't say that I am an expert to be able to speak about it, but we have an expert today, right?
Dr. Jeff Creque is co-founder of Marin Carbon Project and director of Rangeland and Agro Ecosystem Management at the Carbon Cycle Institute, where he focuses on carbon farming and land management. Informed by over 35 years of applied experience and theoretical training. He also serves as a technical consultant for the Bolinas, Stinson Beach, and West Marin compost projects. Jeff holds a PhD in rangeland ecology, is a California State Board of Forestry certified professional in rangeland management and technical service provider for the USDA Natural Resources Conservation Service. Jeff farmed organically in Marin County from 1979 through 2013 and has been making and using compost for over 50 years.
50 years, pretty cool.
Mm-hmm.
Okay, I'm going to stop sharing my screen, and then we'll let Jeff come on and do his stuff.
It's always a pleasure to speak with this group because of the work you're all doing and will continue to be doing. And I always like to talk about compost, my favorite subject. This talk deviates a little bit from compost specifically, but I will talk about compost, and I also hope that you'll feel free to answer or to ask and answer any questions that perhaps I can help with around this topic.
And sorry, just to interrupt for a brief moment. We're going to do the same process as we did with last week's speaker. So Melissa's going to monitor the chat. And so Jeff, if there looks like there's something where people are confused by a topic you're talking about, then she'll flag you and ask for clarification. Otherwise, then, every 30 minutes or something, when you think that it's a good time to stop, then we'll then have people use the raise their hands function on Zoom, and then we can get to some of the questions. So sorry to break your stride there.
No, not at all. And maybe you can keep me on track as far as time as well. Okay, so this nexus between compost, soil, carbon, water, and climate is a critical one at this juncture. And I put this up here, continuing lessons from the Marin Carbon Project and beyond, because we learned a lot from the Marin Carbon Project work, and we continue to learn from that work. But we've also expanded that work and taken it beyond Marin County and have learned quite a bit in the process of doing that as well. So just briefly, the Carbon Cycle Institute, with whom I'm currently working, is really about advancing the carbon cycle as an organizing principle or organizing concept underlying land management and on-farm conservation in our efforts to mitigate and adapt to the global climate crisis. And again, this nexus between the climate, the carbon cycle, and our land management activities is critical in what I'm going to focus on today. Why the focus on carbon? Well, carbon, it turns out, is the energy currency of all living systems on the planet, and it's connected, therefore, to all aspects of the human enterprise. In the context of catastrophic climate destabilization, our focus is necessarily on the global carbon cycle, and particularly this nexus among the atmosphere, the soil, and the well-being of all of us and all global inhabitants. This quote from Edward Teller, I think, is telling. It's particularly telling, I think, in light of the recent revelation that Exxon executives and scientists have known about the impacts of burning fossil fuels since at least the 1970s. And in fact, we've known that impact was taking place much before that. Edward Teller addressed Congress in 1959 and pointed out that carbon dioxide has this strange property. It's able to transmit visible light, but it absorbs the infrared radiation which is emitted from the Earth. Its presence in the atmosphere causes a greenhouse effect. It's been calculated that a temperature rise corresponding to a 10% increase in carbon dioxide will be sufficient to melt the ice cap and submerge New York. This is more serious than most people tend to believe. So we really have absolutely no excuse that we find ourselves in the position we are, but nevertheless, here we are. Of course, Teller was advocating for nuclear power, and this is why he was addressing Congress and describing the hazards of burning fossil fuels. But nevertheless, he was I wouldn't say prescient. He was a physicist, and he had done the math, and he knew exactly what was coming. This is a little bit of a story that I think probably most of you have heard, probably in your high school biology class or earlier. So the Flemish chemist von Helmont asked the simple question, where do plants get their mass? And to address that question, he decided he planted a willow sprig in a pot, and then he grew that willow on for 5 years, and he provided nothing to that growing plant except additional water. And having weighed the soil at the beginning of the experiment, and then at the end of the experiment, while the tree had gained 75 kilograms in weight, the soil had only diminished by about 60 grams. So about 1,000 times more weight in that tree than was removed from the soil in the pot. And von Helmont, given the time and the resources he had available to him, had to assume, therefore, the mass of vegetation is derived from water. Clearly, it's the only place it could have come from. Of course, he was wrong, and we learned this from subsequent work done by a couple of additional chemists, European chemists, Sprengel being one of them. Sprengel was really the first to formulate the theory of minimum in agricultural chemistry, which in this theory says that plant growth is limited by whatever essential nutrient is most lacking. And that no matter what you do, unless you address that single gap in plant nutrition, you won't be able to advance or enhance plant growth. What this did was to take Albert Thayer's theory of humus and basically throw it out, make it irrelevant. Thayer was a renowned European agronomist. He published his 4-volume Principles of Rational Agriculture in 1809, and his humus theory assumed that plants derive their mass from soil humus, that somehow plants are taking up humus and they're transforming it into their biomass. So again, this was subsequently refuted essentially by Sprengel's theory, and then further refuted, if you will, by Justus von Liebig. Now, Liebig was an interesting character because Liebig not only further elaborated on Sprengel's work, but he also was the first to actually demonstrate that plants obtain their carbon from the atmosphere. Now, that was critically important information. At the same time, Liebig was also developing the first commercial fertilizers based on this theory of minimum, and developed a very productive artificial fertilizer industry in England in the 1840s. The timing was perfect because at about that time, London had just begun to divert its human waste from its agricultural fields surrounding the city into the River Thames. And this was considered a great advance in sanitation at the time, of course, but the result was to divert a large volume of nutrients away from agricultural soils, and ultimately essentially began the decline of soil fertility in the Western world. This is documented in this article from the London Farmers Magazine of 1840. I won't bore you with reading it, but the point here is that this very nutrient-rich material is now going away from our farmlands and into our rivers. To me, this begs the question, then, what is organic farming? And I think it's important to understand that this chemical view of soil fertility that was rooted in Sprengel and Liebig's work, based on this law of the minimum, had begun by the 1920s to manifest in declining soil fertility, declining seed fertility, and declining livestock health and fertility. And a group of farmers, European farmers, became very concerned about this, and in 1922 and 23 approached philosopher Rudolf Steiner for assistance in addressing what they were observing. So in 1924, Rudolf Steiner gave his series of 8 lectures in Silesia, at Koberwitz in Silesia, Silesia being now southwestern Poland. And over the course of this week, he gave a series of lectures which became the foundation for biodynamic agriculture. And if you're interested in this, you can read Steiner's little book called Agriculture, and which contains these lectures. And it's a fascinating read. It's a little difficult to wrap your head around Steiner's philosophy, but very interesting. But in any case, this resulted in a real shift in thinking among a certain group of farmers. Now, in 1911, Frederick King had already published Farmers of 40 Centuries, which was a very interesting treatise on his work in Asia. He had traveled throughout, particularly China, asking the question, how is it that this huge population of folks had been able to maintain soil fertility for literally 4,000 years? And at about that same time, Steiner, of course, was giving his lectures, but Sir Albert Howard, who was a British mycologist, serving at the behest of the royal family, was working in India, conducting compost experiments at indoor India, and adapting what were really traditional Indian methods of soil quality improvement to the demands of British colonial plantation agriculture. Sir Albert published his work in a couple of books, Agricultural Testament and The Soil and Health, and these had a profound impact on Lady Eve Balfour and Franz Sykes, who then formed the Soil Association of Britain. At the same time, J.I. Rodale was reading Howard's work and began the American organic farming and gardening movement in the United States. I'll point out that a student of Steiner's, Alan Chadwick, came to California in the 1960s, started the UC Santa Cruz Farm and Garden Project, and went on to form a number of gardens across the state of California and train hundreds of students in his biodynamic French intensive horticultural method. And Chadwick also helped develop the Green Gulch Zen Center farm. And that's where Chadwick died in 1984. And that's a whole nother story in itself, which is worth exploring at some point. All of this work in organic farming, the early organic farming years, was really, I think, precipitated and advanced by the disaster of the Dust Bowl era. So this is from 1935 in Baca County, Colorado, Dodge City, Kansas. This was a horrific event, and literally many people thought that the world was coming to an end. This event in Liberal, Kansas, this dust actually reached Washington, D.C. And at the time that this was taking place, the question of whether or not to form the Soil Conservation Service was being debated in Congress. And as the dust, the timing, I think, was not accidental. As the dust was settling over the Capitol, this debate was going on. And subsequently, of course, the Soil Conservation Service was indeed formed. Ultimately, that work, the work of the Natural Resources, what is now the Natural Resources Conservation Service, resolved this problem, at least for the time. What's interesting to note, however, is that very recent work has identified the Dust Bowl as a very early symptom of global warming, that the intensity of the Dust Bowl events were aggravated by what had already been a slight increase in global mean temperature, which contributed to the drought and to the subsequent Dust Bowl catastrophe. So I think it's critical in talking about this phenomenon and this work that we understand the carbon cycle to the extent that we can understand the carbon cycle. This is a big cycle, it engages the entire planet. And what's interesting is that carbon on planet Earth occurs in 5 major pools. Of course, we're all familiar with the fossil pool, oil and gas and coal, the atmospheric pool, the marine pool, the aquatic pool, vegetation, and soils. As carbon moves among these pools, and it does on both short and long time scales, it changes form. So as we burn coal, for example, we transform carbon from this lithic pool into a gas, carbon dioxide, which of course is causing our warming conditions. But as carbon dioxide then is absorbed by the oceans, carbon dioxide from the atmosphere is absorbed by the oceans, oceans acidify, because as carbon dioxide enters water, it becomes carbonic acid. And so we see our oceans acidifying as well as warming in response to this situation. A number of folks, many folks, in fact, very common to hear folks talk about planting trees, planting forests as a solution to the climate crisis. As those of us in the West are all too familiar, our forests, at least in the Western United States, have a nasty habit of sending their carbon back to the atmosphere in rather catastrophic events, which really leads us really only one place where we could potentially park this extra carbon dioxide, and that is our soils. And the beauty of soils, of course, is that as we increase their carbon content, almost without exception, we see positive changes in the soil and in the resulting plant growth in response to increasing carbon in our soils. So soils are the biggest or second biggest carbon pool on the planet, and have the potential to store much more carbon than they already do. Another aspect to all of this, which is really, in many ways, equally disturbing is that not only have we radically increased the carbon content of the atmosphere through our fossil fuel combustion, but we have also reduced the capacity of the biosphere to absorb that CO2. So what this graph shows, and this is from work by Shramsky and others, and this is a fascinating read, but essentially what you're seeing here is that 2,000 years ago, we had, given the human population at that time, we had about 70,000 years of phytomass available. That is, we could support ourselves for about 70,000 years on the plant biomass on the planet 2,000 years ago. But today we only have about, at best, 1,000 years of phytomass, given the human population trends and given our destruction of the global capacity to absorb CO2 from the atmosphere. So these are just very, 4 examples from 4 different parts of the world, demonstrating the extent to which we have eliminated the capacity of planet Earth to balance itself out, to absorb CO2 from the atmosphere and transform it into biodiversity and fertile soils and all the biocomplexity of the planet. So a very disturbing trend. We're essentially burning the candle at both ends. We're adding CO2 to the atmosphere by burning fossil fuels, and we're eliminating the capacity of the biosphere to reabsorb that CO2 and create fertile, productive landscapes. So this is a fairly recent image from the Scripps Institute showing the record of rising CO2 levels in the atmosphere. This is actual data from the top of a Mauna Loa volcano. This is the Keeling curve. Probably most of you are familiar with this, but you can see what's happening to CO2 levels in the atmosphere just in the last 50 years or so, 60 years, 50, 40, 60, yeah, 60 years. 420 parts per million is, whoops, sorry about that. I'm not sure what happened there. Are you still able to see that?
Yeah.
Okay, great. This is not, oh, I see what happened. Sorry. There we are. I went back to the website. This shift, this incredibly rapid rise in carbon dioxide levels in the atmosphere is, as we know, driven largely by the combustion of fossil fuels. But there's another piece to this, and that is that this trend in rising carbon dioxide levels is paralleled by the rising loss of carbon from our soils globally. And this is work by Sanderman and others showing the loss of carbon from our grazing lands and our croplands over the last couple thousand years. A slow and steady climb in losses as agriculture advanced across the globe. But with the dawn of the Industrial Revolution, around 1750 or so, we begin to see a very rapid increase in losses of carbon. So not only are we adding carbon to the atmosphere from fossil fuel combustion, we're also adding carbon to the atmosphere from our management, or we could say our mismanagement of our soils. So again, burning the candle at both ends. The result of this is the more or less universal degradation of our soils globally. The only soils that aren't showing degradation are either true desert or covered with ice or snow, although that's obviously changing very quickly. This quote from 2014, so almost 10 years ago now, suggests that during the last 40 years, nearly a third of the world's arable land has been lost to erosion, and it continues to be lost at a rate of more than 10 million hectares per year. So huge impact that we're having on the planet. Looking just at irrigated lands, about 62% is degraded, 38% is in good condition. So again, with a a rapidly rising human population and a rapidly degrading biosphere, our future does not look too bright at this moment. Let's see if I can get rid of this. Oh yeah, there we go. Okay. So what is the role of soils in climate change mitigation? As I mentioned earlier, healthy soils can store an awful lot of carbon. Upwards of 300 tons per hectare is entirely reasonable. That's about 1,100 tons of carbon dioxide equivalent per hectare. Hectare is 2.5 acres roughly. 2 billion hectares of degraded land worldwide, an area larger than South America, have the potential for rehabilitation and carbon restoration. And restoring our soils has the potential to store up to 3 billion tons of carbon annually, which is equivalent to about 30% of our annual carbon dioxide fossil fuel emissions. So a very, very significant potential for our soils to store more carbon. I'm going to very briefly touch on general systems theory because this has been very helpful in my own understanding of this work, and I think this is useful framework for this work. Very simply, general systems theory suggests that systems, we mentioned agroecosystems at the beginning of this talk, systems of any kind, whether it's a garden, a farm, or a global system, they're either changing or they're staying the same. And that's pretty simple to understand. The question, though, is how do systems stay the same and how do they change? So it turns out that system stasis or equilibrium is maintained through deviation dampening negative feedbacks. What does that mean? Well, it means that the system, as the system moves away from some central tendency, something takes place that pushes it back. Some negative feedback pushes it back toward that central tendency. And then again, as it moves away from that central tendency, somehow it's pushed back toward that central tendency. So what we call equilibrium is really a dynamic equilibrium with a fluctuating around some mean system state. On the other hand, system change is driven by what are known as deviation amplifying positive feedbacks, which drive directional change. So we go from a state of homeostasis through some transition driven by some impact that is causing greater and greater movement away from that central tendency. And then we may find ourselves at some new homeostasis at a higher or lower level of system organization, but we have clearly changed the system. A classic example of a negative feedback is the way a thermostat works. So as a room cools down, the thermostat at some set temperature kicks on the heat and the room begins to warm up again. And then at some temperature threshold, the thermostat recognizes that the temperature is adequate and it turns off the heat, and the room then gradually begins to cool. And again, at some lower threshold, the thermostat kicks on the heat and the room is warmed again. So this is maintaining a steady state through a dynamic equilibrium driven by negative feedbacks. As too hot, thermostat kicks off the heat. Too cold, thermostat kicks on the heat. And we stay in this nice zone of equilibrium we call a comfortable room temperature. Positive feedbacks are sadly demonstrated very clearly in current global dynamics. So we can see in the case of the Arctic ice cap that when we look at 1979 compared to 2021, clearly ice is diminishing in the northern hemisphere. As ice melts, of course, due to global warming, we see more dark water exposed at the pole. Now, dark water can obviously absorb more solar radiation than can ice or snow. And so we see a warming Arctic Ocean in response to this more dark water. which of course drives more melting of ice, which will expose more dark water, which will further melt additional ice, which will expose more dark water. And so we're on this runaway positive feedback trend, if you will, what we can call steady flow dynamics, but the system is continuing to change in the same direction and therefore is moving away from equilibrium towards some new higher, or perhaps we could say lower system state. This is also reflected somewhat alarmingly in the record of carbon dioxide levels in our atmosphere, going back 800,000 years and actually going back 3 million years. We have seen what is recognizably a state of dynamic equilibrium in carbon dioxide levels in the atmosphere. It's not a perfect relationship, but we see that overall carbon dioxide has fluctuated between about 190 and 290 parts per million for the last 3 million years. What seems to be driving this is the angle of the Earth in relationship to the sun and the proximity of the Earth in relationship to the sun. As the northern hemisphere tilts towards the sun, there's more solar radiation available to drive additional plant growth, and we see a drawdown of CO2 from the atmosphere as plants grow and draw down that CO2. As we tilt away and less plant growth is taking place in the northern hemisphere, then that some of that CO2 is then re-emitted, and we see a cooling of the global atmosphere. So this trend in rising and falling CO2 levels has kept us in a rather comfortable planetary state for a very long time. Unfortunately, we're sitting up here at 420 parts per million today, and we'll probably hit about 422, possibly even 423 by the summer of this year. So, clearly understanding a little bit of systems theory helps us recognize that this is a truly dramatic system change, and one that we should probably be paying very close attention to, and doing all we can to draw that CO2 out of the atmosphere and try to get us back down at least to maybe around this 290 upper level that we've seen historically. Carbon dioxide is, of course, not the only greenhouse gas. And maybe I should stop briefly if anybody has any questions specifically about
They do.
Yeah, okay.
Do you want me to read them to you?
Sure, that'd be great. And everyone
Okay. What's your opinion of the contribution of the cattle industry to the carbon climate change crisis?
I think it's, I will get into that a little bit more in detail. So maybe I'll defer that question until I'm actually talking about methane.
Okay, and what is dark water?
Dark water is, well, in that image particularly, I'm simply comparing the color of the ocean, the Arctic Ocean, to the color of the ice cap. So we're looking at dark blue water, which is absorbing solar radiation much more efficiently than white ice or white snow.
Okay, and someone's asking, is this the Steiner book mentioned, Rudolf Steiner ebook on Amazon?
I don't know. Is it called Agriculture?
Yes, that's broken up. Agriculture, Rudolf Steiner.
Yep, that's it.
Okay, and is the shift driven by fossil fuels?
Is this in reference to, well, I assume so, yeah. Yes, fossil fuels is far and away the driver of this shift. Absolutely. And we know that because the science is very clear on that basis, yeah.
Can you define photomass?
Phytomass?
Phytomass.
Yeah, basically plant material. So plant matter, plant mass.
Okay. Parallel by, okay. I'm sorry, Lori, I didn't read your whole statement. shift driven by fossil fuels, paralleled by rising loss of carbon.
Yeah, what I tried to show in that slide was that about a third of the excess carbon dioxide in the atmosphere is actually coming from our land management practices, including the degradation of our soils, but also the cutting down of our forests, the burning of our forests, and so forth. But yeah, our land management practices are contributing significantly to this overall problem.
And that does it for the questions.
Okay, great. Thank you. Good questions. So there are other drivers, of course, of climate change besides carbon dioxide. Here you can see the Keeling curve on the upper left, but nitrous oxide is also rapidly increasing in the atmosphere. Methane is rapidly increasing in the atmosphere. And these man-made gases on the lower right seem to be coming under control. We're seeing the closing of the ozone hole, which was a result of our use of CFCs. We still have some other man-made gases that are contributing, but we more or less have those largely under control in terms of their heating potential. But methane, nitrous oxide, and carbon dioxide are the big monsters in the room as far as global warming. When we put the impacts of those three gases together, which NOAA does to develop this annual greenhouse gas index, we see that overall we've increased greenhouse gases in the atmosphere by about 49% since 1990. So the greenhouse gas index is 1.49, using 1990 as the baseline. So the actual carbon dioxide equivalent of these gases all combined brings us not to 420 parts per million, but to 510 parts per million. And that is the warming impact that we're facing right now. So as bad as 420 is, 510 is obviously much worse. And I think that helps explain why this statement from Professor Adam Scaife, which was made in The Guardian just the other day, he says the probability of having the first year at 1.5 degrees Celsius in the next 5-year period is now about 50-50. And what he's referring to there is that, as some of you will remember, in the Conference of Parties back in 2015, it was decided in Paris that we really needed to keep our warming below 1.5 degrees Celsius. And there was a lot of controversy around that and a big fight about that, because at that point, folks were talking about a 2 degrees Celsius as a permissible rise in temperature. And we're now, I suspect, the fact that Professor Scaife said this suggests to me that before 5 years is up, we will see a 1.5 degrees Celsius warming overall on the planet. Now, parts of the planet have already warmed well beyond 1.4 degrees Celsius. This is just a global average temperature. But given the climate disruption that we've already experienced and are experiencing globally, and certainly we're seeing it in California, both in our droughts and our atmospheric rivers, 1.5 degrees Celsius, in other words, warming more than we've already experienced, is not even an acceptable level. But we're going to get there. That's where we're going. And at this point, we're slated to hit about 2.8 degrees Celsius by 2050, unless we make some radical changes very quickly. At this point, anthropogenic climate change is really irreversible, unless, and the only way it could be reversed is if we could remove a large amount of carbon dioxide from the atmosphere and sustain that removal over a long period of time. And that's from the Intergovernmental Panel on Climate Change. As I mentioned earlier, cultivation and fertilization of our ag lands has reduced soil organic carbon content and by over 1,000 teragrams. That is essentially 1 billion metric tons of carbon, which has essentially ended up in the atmosphere as carbon dioxide. Somewhat ironically, agriculture is really probably the most vulnerable sector with regard to climate change. If you think about it, not being able to rely on when that first frost date is going to come, or when your final frost date is going to come, or when it's going to rain, or how much it's going to rain. Not to have that basic understanding of your farm system radically complicates the farming exercise. It makes it much more difficult to succeed, to successfully produce crops. And we're seeing that, of course, all over the planet with failing crops and flooding and drought and so forth. As noted by the executive director of the Institute for European Environmental Policy at COP22 in 2016, enhancing soil carbon is the only viable option to achieve negative emissions, that is, to achieve drawdown of carbon dioxide from the atmosphere. Now, this is work by James Hansen and others, published a couple of years ago. Essentially, what this is telling us is that we have to draw down carbon dioxide as well as ceasing emissions. If we look at the graph on the left, this assumes no drawdown of carbon dioxide, but varying levels of emission reductions. The rapidly rising red line assumes a 2% increase in emissions, which frankly is about what we're doing right now. In fact, I think we're doing a little worse than this. The two declining lines suggest a reduction in emissions of between 3% and the optimal line there, 6%. And there was a time when I would have thought this was virtually impossible, but in fact, during the first year of COVID, we saw a 7% decline in global emissions, which was really good news. If you were looking for a silver lining to the COVID epidemic, this is it. And what that tells us, I think, is that, as tragic as the COVID scene has been, and the many millions of people who've died, in terms of total global disruption, that 7% decline was relatively without major impact. We got through that, and unfortunately, we've reverted to our old habits. But I think it tells us that we could, in fact, achieve this level of emission reduction without radical disruption of planetary human activity. If we add carbon dioxide extraction from the atmosphere to that equation, we do a much better job of drawing down carbon dioxide from the atmosphere, and we do it much more quickly, so that by the end of the century, we could be sitting at about 350 parts per million, which Bill McKibben's group, 350.org, suggests is a safe level. I would suggest it's not a safe level, given historical, ice core data showing us that 290 is really where we should be at maximum with our carbon dioxide levels. But 350 is sure a whole lot better than 420. And we could do this. We could do this with a combination of ceasing emissions and drawing down carbon dioxide. But even a 6% annual reduction in emissions is not enough to get us back to a safe level. We have to draw down CO2 in addition to eliminating our greenhouse gas emissions. So the tool for doing that, I'd suggest, and many others have suggested, is agriculture. Because agriculture fundamentally, as my friend John Wick from the Marin Carbon Project has noted, agriculture is the art of moving carbon among the carbon pools to produce the food, fuel, fiber, and flora that we all depend on. The mechanism, of course, is photosynthesis. Photosynthesis is the synthesis of carbohydrates from sunlight, carbon dioxide, and water. It is the transformation of solar radiation into biochemical energy. It's in a very real sense a magical process upon which all life on Earth depends. So plants, derive all of their carbon from the atmosphere, from the air. And they do so through this photosynthetic process using solar energy as the energy source to combine atmospheric CO2 with water and minerals, and to produce their biomass. importantly, and something we don't always think about, is that much of the sugars that plants produce in the process of photosynthesis actually ends up in the soil. The plants are discharging carbohydrates into the soil environment all the time. And as much as 40% of plant photosynthate actually ends up in the rhizosphere, the zone around the plant root. Now, why in the world would plants expend up to 40% of their energy simply discharging what Christine Jones, a soil scientist from Australia, has called the liquid carbon pathway to the soil? Why would they contribute it to the zone around the roots? Well, plants are trading photosynthate, simple sugars. They're trading that to the soil environment in exchange for nutrients, minerals, enzymes, and other beneficial materials from the soil biology that surrounds this incredibly complex zone. The most intensely complex biological zone in the soil is right around the plant root. And that is because the plant is feeding the soil with solar energy in the form of simple sugars. So this is a critically important piece of this equation that we often forget about, that yes, plants are drawing minerals and water from the soil, but they are actually feeding the soil at the same time that they're growing. And it's critically important that we understand that relationship. Part of that is this incredible symbiotic relationship that we call mycorrhizae. It's interesting because Sir Albert Howard, in his early work, had identified up to 20, he speculated that up to 20% of plants on the planet were existing in relationship with a root fungus in this mycorrhizal association. As it turns out, it's more like 90% of the plants on the planet have this relationship with various fungi. Now, the beauty of this relationship is that the root and the fungus become intimately associated, and the mycorrhiza, the root, provides the fungus with sugars, again, solar energy, but in return receives a much expanded root system in the form of the fungal hyphae that are living in association with the root. So this enhances water uptake, it enhances phosphorus uptake, and we've only recently learned about this material called glomalin, which provides a carbonaceous sheath around the growing fungal hyphae and provides an enormous contribution to soil carbon. So this is a photograph of what's known as a arbuscule or endomycorrhizal arbuscule within a plant root. We're actually inside the plant root, and we're seeing this fungus, which is growing beneficially inside the plant root. And you can see these finely branched mycorrhizal features in which this exchange of sugars from the plant to the fungus and from the fungus to the plant is taking place. We have other interesting relationships in the rhizosphere. There's rhizobium. I think most of us are familiar with rhizobium and the capacity of this association between plants and microbes to provide nitrogen to plants through the fixation by the rhizobial bacteria of atmospheric nitrogen, and then making that available in usable form to the growing plant. There are also some actinorhizal species in which actinomycetes form symbiotic relationships with roots, in this case an alder, in which nitrogen fixation is also taking place. The fungus or the actinomycete is fixing the nitrogen and then subsequently making it available to the plant root. This incredible biodiversity is something that we really have only begun to appreciate in relatively recent time. On the left, you see a micrograph of a root in association with hyphae, fungal hyphae, and on the right, you can see that if you look at this, looks like a little pine tree seedling. There's a yellowish brown root that is the pine root. But then all of this fine, what seem to be root hairs surrounding that, is actually fungal hyphae. It's not the root, but you can see that it effectively increases the root absorption area by anywhere from 10 to 1,000 times. Also, plants can, because mycorrhizae are relatively, shall we say, promiscuous, in that they will tend to associate with almost any plant species. Groups of mycorrhizae will associate with any different, many different plants. And so you can actually get mycorrhizal connections between plant species. You can have an intimate connection between, say, a plant in one position in the garden soil and a plant next to it or adjacent to it. They can actually be physically connected through this hyphal relationship. So critically important relationship within the soil. I mentioned glomalin. This was only discovered in 1996 by Sarah Wright at USDA. This is a proteinaceous and carbonaceous sheath that surrounds the fungal hyphae. And as the fungus is growing, sending its hyphae through the soil environment, it's exuding this proteinaceous carbonaceous sheath as a protection, if you will, for that growing hyphae. And upwards of 40% of the carbon in the soil is being derived from this phenomenon, from the growing mycorrhizal glomalin feed. So this is something we only recently learned about, and it turns out to be critically important to soil carbon, which of course raises questions about how we manage our soils and to what end. Aldo Leopold in 1949 said that fertility is the ability of soil to receive, store, and release energy. So again, we're talking about that transfer of solar radiation into the soil environment where it can feed the soil biota. And it's the soil biota, it's this biologically active soil driven by carbon, which allows for the biodiversity of the soil, allows for soil aggregation, because soil aggregation, which is the formation of distinct units within the soil mass, it requires energy for that structure to take place. And that energy is generally provided by biological activity, which is energized by carbon, which is derived from plant root exudates and organic matter, which ultimately derives its energy from the sun through the process of photosynthesis. So a really dynamic and totally essential process taking place on the planet. So basically what I just said, we're talking about managing, when we talk about managing soil organic matter, we're talking about managing the flow of solar radiation through our farm system. We've got our hand, if you will, on the lever, the most powerful lever we could have, because we're determining how much of the sunlight that's striking our growing vegetation is actually going to be conserved and channeled through the garden food web or the farm food web. So plants absorb the sunlight, they provide 40% of that energy that they used for their photosynthate ends up in the soil. Of course, animals eat plants and vegetation, that energy then is transferred to animals. The soil biota then supports all of this other biodiversity. So if we want to enhance biodiversity planetarily, we need to be thinking about how we're going to capture more solar radiation and transform it into plant biomass and subsequently into the food web. So I hope by now I've at least given you a sense that carbon is really the key to agricultural productivity and resilience. And this is a great schematic by Dr. Nicasio out of Minnesota, out of the ARS, Ag Research Service in Minnesota, in which he puts carbon as a keystone element in all of these, in this relationship with other soil nutrients. And so in a way, kind of bringing, that Thayer framework along with Sprengel and Liebig, bringing them all together, but with the understanding that carbon isn't just an element, it's the keystone element, because it is providing the energy for all of the processes that drive agricultural production and resilience. Questions?
Yes, there is one question, and that is the rhizosphere also called the crown?
No. The crown is simply that part of the plant where the stem meets the root, right? That's a part of the plant. The rhizosphere is a ecosystem that includes the root, the entire root, all of the root. It includes the mycorrhizal association with the root and all the biology within that mass. So when I showed that picture of an uprooted plant, it's that whole thing. It's all of it. It's the soil, it's the root, it's the mycorrhizae, it's all the bacteria and micro critters that are living in there. It's that it is an ecosystem in itself, literally. It is its own ecology right there. It's surrounding that plant root. So it's all of it. This is kind of the background that I've just given you, underlying the thinking behind the Marin Carbon Project. Back in 2006, John Wick and I were having a conversation about agriculture and the climate. And the question was, could Marin's grassland agriculture be a carbon sink, be an opportunity for drawing carbon dioxide from the atmosphere? Could we build soil carbon in Marin County at the expense of the atmospheric CO2 load? And partnering with a whole bunch of local ag agencies, from the RCD to the NRCS to then Marin Organic, Malt, and John Wick and Peggy Rathman, we launched this effort to answer that question. We approached Dr. Wendy Silver at UC Berkeley, who was very interested in working with us. One of a dozen scientists we approached. She was the only one who actually had an interest in the work. She had done a lot of work with soil carbon in tropical systems, but had not worked in California. She was very dubious that we could achieve any meaningful results in Marin, which we thought was a great opportunity. Perfect scientist, a skeptical one. And so we launched the project. And fundamentally, very simply, the hypothesis was simply that we could increase soil carbon through management, and that we could measure a change. We knew if we couldn't measure a change in soil carbon, then we weren't going to be able to have a story to tell. So then the question was, well, how do you test this hypothesis? And based on my decades of work with compost, I said, well, why don't we just add some carbon to the system and then come back and see if we can measure a change? Very, very simple hypothesis test. And so to add some carbon to the system, we put 1/2 inch of compost out on standing vegetation on grazed grasslands in Marin County, and we replicated this up in the Sierra foothills, as shown here at the University of California experiment station at Browns Valley. And then Dr. Becca Riles, now Dr. Becca Riles, who was a grad student with Dr. Silver at the time, conducted her doctoral dissertation research on the results. And I will say that Becca Riles has gone on to do some great work at UC Merced, where she's now a professor, and continuing along these lines of research. In any case, this is 1/2 inch of compost going out on the ground in 2008. The first spring of the year, this is the first thing we saw, was that the cows were gravitating to the compost treated plots, which was very humorous to see. But when we actually sent the forage to the lab, we found that the compost treated plots had higher protein in the forage growing on those plots, and the cows were sensing that, and they were enjoying themselves on those treated plots at greater extent than on the non-treated plots. The next thing we saw was that there was more of that higher quality forage. At both sites, we saw a significant increase in forage production. Now, what is forage production? What is forage production? Well, forage production, an increase in forage production, means that we're capturing more carbon from the atmosphere and growing more grass, right? And some of that presumably ends up in the soil. And in fact, we found that we did get more organic carbon in the soils. And as you can see on the compost treated plots, more carbon. Now you could say, well, that's obvious. You added carbon in the form of compost. Of course, you're going to have more carbon on those soils, but this is the compost, this is the soil carbon with the compost carbon removed. And so we saw more carbon in the soil independent of, or above and beyond, I should say, the compost itself. And again, that's reflected in that higher plant growth, which is drawing down more CO2 to produce this additional forage above ground, but that is also having an effect below ground as well. And that's what this data shows. I take you back to the systems theory discussion and look at this graph. And when I saw this, I have to say this is when what had been the missing piece for me in my understanding of this work, this is when it all came together for me, because what this shows is, on the one hand, this hockey stick curve. This is the compost decay curve. And so at the very top here, you see that big slug of carbon going into the system in the form of compost. And then that compost gradually decomposes over time. And so by year, by year 80 or so, we don't have a lot of that compost left. That's a pretty long persistence for that compost, by the way, but remember, this is a grazed permanent grassland system. This is not tilled soil. So that compost persists it decays rapidly, but it persists for quite a long time. What is much more interesting, though, is what's happening in the background, because this is the ecosystem response to that big slug of solar energy going into the system in year one. This is a slow and steady increase in ecosystem carbon in response to a one-time application of compost. And what you see is the system building on itself in a series of positive feedbacks, driving directional change in soil carbon for decades before we begin to see a gradual decline in ecosystem carbon. That is to say, a combination of both vegetation and soil carbon. So what's happening here? Well, as we saw in the data, and we now have 10 years of data showing this, by adding compost to the system, we enhanced plant growth, which means we captured more carbon from the atmosphere, and some of that carbon ended up in the soil as additional carbon. That in turn improves soil fertility and improves water holding capacity of the soil, which enables further plant growth in subsequent years. And so each year we're adding a little bit more carbon from the atmosphere to the soil, simply from that one-time enhancement in soil fertility and organic matter content with the original compost application. So again, this positive feedback process continues, according to the model, for a good 40 or 50 years before it begins to gradually decline. And we could ask the question, well, what happens if we reapply compost, let's say in year 50, let's reapply some compost. Could we drive the system to even a higher level of carbon content and higher level of production? And I think the answer is almost certainly yes, but we haven't had the time to do that yet. This work has been repeated across California on 15 different sites. This is some of that data showing very, very similar patterns. Adding compost in year one, you see the sudden rise in system carbon, and a gradual decline, but a net impact is shown in the blue. Gross impact is shown in green, net impact in blue. Greenhouse gas emissions associated with adding compost to the system draw down the total a little bit, but the net effect is very large and continues again for decades, again, modeled decades, showing that this effect seems to be happening on 15 different sites in California, very different soil types, very different climatic regimes. The pattern is the same, and it's consistent with what we know from systems theory about how systems change, that when we add energy to the system, we can drive system change. And compost, in this case, is that energy. It's the embodied solar energy that was transformed into plant matter and then into compost, and then was re-added to the soil and provided energy to the soil processes and enabled additional plant growth, which enabled additional drawdown of carbon from the atmosphere. So a wonderful complete cycle that is beneficial, particularly from the perspective of climate change. This is just quoting from Dr. Meyer and Dr. Silver's published work on this topic. They conservatively estimate that applying compost to only 6% of California's rangelands would sequester a cumulative 8.4 to 8.7 million metric tons of carbon dioxide at maximum sequestration at year 15. This does not include the carbon and the greenhouse gas savings from diverting organics away from landfill. Okay, so we're not even counting the avoided methane emissions, for example, from diverting organics from landfill to compost production. This is just the enhanced photosynthetic capture from the atmosphere. Now, this alone would achieve about half of the California Air Resources Board's 2022 goal, which is to sequester 20 million metric tons of CO2 by 2030. In other words, the California Air Resources Board is lowballing by at least an order of magnitude what we could achieve in California if we took this process seriously and applied it at scale. They also note that on the two driest sites, Santa Barbara and Tulare sites, they saw a greater carbon benefit of the compost application, and they attribute this to what they believe is an increase in soil moisture, which had a greater effect in the drier sites than it did in the more mesic sites, or the wetter sites. Now, Dr. Marcia DeLange, who was a postdoc at Dr. Silver's lab at the time of the Marin Carbon Project original research, did a full life cycle assessment on compost and compost application on rangelands. And what she shows here, and you see these three blocks of data here: compost on the left, manure in the middle, and fertilizer, synthetic fertilizer on the right. She's comparing their greenhouse gas emissions of using these various materials. And you can see that manure and fertilizer have significant greenhouse gas impacts. Compost also has some greenhouse gas impacts, some emissions associated with it, but the net effect of one, diverting from landfill, which is this avoided emissions in gray, and then the additional, in blue, the avoided emissions are in blue, and then the net effect is in gray. And you can see that compost, if applied to 5% of California rangelands, would essentially offset all the emissions from the commercial sector and go a long way toward offsetting the emissions from agriculture and forestry. Now, this is 2008 data at this point. So very significant potential when we combine the avoided emissions from landfill diversion with the photosynthetic capture of enhanced photosynthetic capture of carbon from the atmosphere. Very significant. Again, about 20 plus million metric tons overall from this 5%. Now that alone right there exceeds the Air Board's objective of drawdown from California and as expressed in their recently released 2030 scoping plan. Now, in case you hadn't noticed, things are getting warmer in California. And this is data, fairly recent data from Pathic and others. You can see that this is departure from mean temperature. So this 0 is our average, long-term average temperature in California. And then years of departure from that going all the way back to 1900. And you can see this steady increase in the years that are hotter than our historical average. That is having a direct impact on crop production in California. This is, you can see modeled impacts here through the end of the century, but we're already beginning to see declines in the abandonment of at least 500,000 acres of agricultural land in California already, and undoubtedly more to come given current trends. As you can see, some crops are more affected than others. But nevertheless, the long-term trends under a warming climate scenario are not particularly positive. The California Energy Commission produces this agricultural vulnerability index. This integrates a bunch of different variables, including climate, the type of crop, the land use, and as well as socioeconomic vulnerability. But you see the image on the right. The Central Valley in particular, that is to say our prime agricultural production areas, fall into the moderately high or very high vulnerability index range. And part of this is the graph on the left showing increasing salinity in California soils, which is not without historical precedent in irrigated agricultural systems. And some of you may be familiar, for example, with the history of the Fertile Crescent. Is a very productive irrigated agriculture region some 2,000 years ago, which succumbed to drought and soil salinity due to overuse of saline irrigated water. So the trends, again, in terms of California's agriculture are not looking too good. And I should have paused over the last group of slides for more questions. I don't know if there are.
Yeah. Oh, that's okay. Let's start with, how do you distinguish between the original compost carbon and the subsequent produced carbon?
Yeah, because we knew exactly how much carbon we had applied in the compost, we were able to subtract that from the total. So based on our controls, that is our untreated baseline condition soil carbon, added the compost to that, but we knew what that was because we actually had applied it ourselves. We subtracted that and then remeasured the soil carbon and found an increase above and beyond the carbon of the compost. That's how that was detected.
And can home gardeners contribute to the increased storage of carbon on a scale that makes a difference?
Absolutely, because there are a lot of home gardeners out there. And when you add it all up, it's a lot. So by all means, no question that thinking about this process and these processes and this potential at the garden scale is critically important. Yeah.
What is the cost to add a half an inch of compost?
Well, are you making it yourself?
Pam, you want to answer? Turn yourself on and answer that. Oh, she's adding a new message. Hang on.
So I'm being a little bit facetious there, but clearly it can be, there can be no cost at all other than a little bit of labor, or half an inch of compost is on a per acre basis is about 70 cubic yards. So a yard of compost these days is going, anywhere from $10 to $40 a yard, depending on whether you're paying for delivery and everything else. So if you're trying to apply half an inch of compost to an acre and you're going to buy it and you're going to have it trucked to you, it's going to be on the order of, could be as high as $2,800. If you're making it yourself, it could be virtually free.
Hello, this is Pam. I have a question. These people that own this rangeland, is it, I know it's a benefit to put the compost in, but financially, are they capable of absorbing that cost?
Right. Yeah. Good question. And the answer generally is no, they are not. But the bigger question, I think, is, are we as a society prepared to absorb the cost? And in fact, the state of California Department of Food and Agriculture is already providing compost to rangelands across the state through the Healthy Soils program. So we have a program now in California which will essentially provide compost for application on cropland, but also on rangelands.
Does the type, meaning the composition of the compost, matter with regard to its efficiency?
I think if we look at the very fine detail of that question, we would probably answer yes, it does matter. But in the very broadest sense, if it's compost, which I will define a little bit later in this talk, if it is compost and meets the definition of compost, then its composition is less important. What does matter, of course, is the carbon content of the compost, and that can vary widely depending on how it's made. So you may have compost that is mostly soil with a very low carbon content, or you may have compost which is very high in organic matter, 25% or higher carbon, which is sort of compost I like to use. But I've seen compost with very low carbon content because so much soil had gotten mixed into that compost in the process of making it, that it was a more mineral material than a organic material.
Do you have any recommendations for compost composition for Marin home gardeners? I am concerned about the smell if I add any kind of manure to my compost.
Yeah, well, if you don't want to use manure, I mean, there are many other sources of nitrogen that you can add to your compost, and kitchen garbage is a pretty good source of nitrogen, actually. Green material, green leaves, green lawn clippings, is a good, are all generally good sources of nitrogenous material. So you don't have to use manure to make compost by any means. And typically, if you're using, garden leavings, green weeds, that kind of thing, that stuff's going to heat up pretty nicely without any additional impetus, really.
What are the factors explaining the difference in the rate of CO2 depletion in different parts of California?
It isn't so much CO2 depletion as it is organic matter depletion. And that is really a function of management. The Central Valley has been intensively managed for over 100 years, and including very intensive cultivation and very little use of organic soil amendments. And so we've basically been mining the organic matter out of our agricultural soils in California to the point where we're now down to about 1% organic matter as an average level in our California cropland soils, which is very, very low.
Are there any technologies which could help to restore the carbon content of soil by absorbing excess CO2 from air?
Yes, it's called photosynthesis.
Okay, and Natalia, I see your hand, but I'm going to cover the rest of the chat before I get to you. So the control was pre-treatment control, not a parallel control?
No, there were both. There was baseline data taken before the compost was applied, and there was subsequently paired plots with controls and treated plots.
Okay. In Marin, can I pick up the finished compost that I dutifully donate every week in my green bin? And if so, where?
That depends. I think the Mount Tam community was providing compost. They were, this has been a couple of years now. They were providing compost to their clients, their green waste clients. I think the other places that your green waste might be going in Marin would probably require you to purchase compost. Now, and I'll get into this a little later. Maybe I can just defer that question because I will touch on this a little bit later.
Okay, and I have an insulated compost bin that holds about 200 gallons. I added a few worms 4 years ago and now have thousands of them and can get a cubic yard of compost every 2 to 3 months. And they're also added, there's a place in Nevada for free compost.
Great.
And I have a question, Jeff, and then Natalia, would you please unmute yourself and ask your question? You mentioned in your presentation that this was done on non-tilled land, and you may be addressing it in your future presentation, but I'm wondering, does the tilling of the land affect the composting and the carbon in the land?
Yeah, very definitely. And I tried to cover that when I talked about, maybe I haven't reached that point yet, talking about cultivation. I will be talking about that impact.
Okay.
Those slides.
Natalia?
Thank you. Thank you. Hello, Jeff. Thank you very much. I find your presentation really fascinating. So my question regarding like the difference between the depletion of carbon and different parts of California referred to one of your charts. You remember those charts where you added carbon and then you tested whether it is going to stay or not, and there is a blue line, like, you know, thick blue line, which depletes differently across California. So that's the question. What's the reason for that? Do you know?
I think maybe that was a misinterpretation of that slide, Natalia, because
Maybe. Yeah.
yeah, I think that was a generalized that was applied across California. It wasn't for different sites across California. It was different materials. So we were comparing compost with manure and fertilizer.
Okay, but the right tail was, like, you know, on the chart was different.
Is this
the one before? No, the one before.
the one before?
Mm-hmm. No,
This
you
one?
have like 6 charts there, like, you know, basically, yeah.
Okay, I'm not going to go back through the whole thing. But,
Okay.
I don't think I was referring to different parts of California. Oh, I think I know what you're saying. You're
It's the
talking about
yield responses one.
Dr. Silver's data.
Yeah.
Yes. This one.
Yes.
Yeah.
Yes.
Okay.
Yeah.
Great.
And to see, like, you know, the right tail is different in all the charts, and it's across California.
Yes. Well,
Yeah.
again, these are different sites, different temperature regimes, different soils. But although there's some subtle differences, I would say these are almost all identical. Honestly, there are slight differences. Emissions are slightly higher in some soils and some areas, which is the red line, are emissions. But the overall effect is very, very similar. So it's really the pattern we're looking at here rather than absolute amounts. But you would expect some variation across soils, across temperature regimes, rainfall regimes. So again, it's a reflection of the differences in climate and the differences in soil across the state.
Okay, thank you. One more clarification with respect to photosynthesis. I understand that, but my question was, well, basically there is a lot of carbon dioxide in the air, right? And that's the reason for the climate change. So is there any industrial, you know, technology which could put it back into the soil and, like, you know, improve the soil and slow down the climate change? And I'm thinking about, like, you know, there is a lot of talk about carbon capture. So yeah, that's my question. Mm-hmm.
Yeah, absolutely. Okay. I will touch on that a little bit later. So thank you for that.
Thank you.
Just a comment, the reading of Pam Pierce's book, Golden Gate Gardening, has detailed information about different ways to make compost.
Great. Good. Thanks for that reference. So this slide obviously is a map, if you will, of the soil organic matter content of California soils, focused obviously on the Central Valley. And you can see that we're not doing too well for soil organic matter content in California, particularly in our most productive agricultural regions. The Soil Conservation Service has suggested that 5% organic matter is an indicator of a healthy soil, and you can see that that means this fairly dark green color. And you can see we do have quite a bit of that on the Central Coast, some in Marin, a little bit in the foothills. But basically, our main production areas in California, the Central Valley, and particularly the San Joaquin, is looking at 1% or even less organic matter. So lots and lots and lots of potential for improvement in that arena, which means there's lots and lots of opportunity to store additional carbon in those soils. Given that previous slide, I think it's entirely valid to ask this question. This image is from Oklahoma in 1935, but I'll tell you, this summer you could have driven down into the San Joaquin Valley and seen images just like this in California. And we should be alarmed by that state of affairs. This is California 2014. This is a dead almond orchard, dead because it could no longer be irrigated. This is looking west. So basically the west side of the San Joaquin Valley. This is where we've abandoned 500,000 acres and more to come, because of two factors: a lack of water and increasing salinity in those soils. Pattern again, that we've seen repeated globally over and over throughout human history. So very alarming situation, and these low organic matter soils are absolutely part of the problem. A part of the problem lies in this curious concept of tolerable soil loss, or T factor. The T factor emerged out of the Dust Bowl era. The Soil Conservation Service, quite reasonably, I think, asked the question: what is the maximum amount of soil that we can lose from every acre of land every year and still have that land remain productive over the long term? And that's the concept of tolerable soil loss was developed. Now, on a national level, the average value for T is 4.33 tons per acre. If you can imagine losing 4 tons of soil off of every acre of land every year, now that's a very small amount in terms of soil depth, probably on the order of the thickness of a dime over an acre of ground. But if you think about it, does tolerable soil loss make any sense at all? What we're doing when we manage for tolerable soil loss is we're managing for an equilibrium state, but we're managing for a degraded equilibrium state, because our soils have already lost so much, both in total soil, but also in soil organic matter, that managing for tolerable soil loss, for stasis in our degraded soils, makes no sense whatsoever. And I think NRCS has come to that realization because in 2011, they put forward this idea: rather than managing for tolerable soil loss, let's manage for soil change. Let's manage for carbon. And you can see what happens when we shift from managing for tolerable soil loss to managing for carbon. We see a significant increase, not only in the soil quality and the organic matter content of our soils, but also in the value of the agricultural products coming off of that land, because fertile soils produce more produce, obviously. So we're talking about shifting from a equilibrium focus that basically talks about equilibrium at a degraded state, and moving the system to some new higher level of production or higher level of organization. And think back to that graphic from the Marin Carbon Project data and realize that we're talking about initiating a steady flow condition, a series of positive feedbacks by enhancing soil carbon, increasing productivity, continuing to enhance soil carbon over time, and move our agricultural systems to a higher productive level and a higher state of fertility. Now, think about the fact that we've been in this down degrading state for the last 150 years or so in the Central Valley of California. What if we had been building soil carbon throughout that time? What if we've been building soil fertility throughout that time? Where would California be today if we had a 150-year history of building soil organic matter instead of 150 years of degrading soil organic matter? So the opportunity ahead of us is vast and really very exciting if we think about it in terms of what kind of a future can we imagine for California soils and California agriculture. Now, the NRCS, again, has said the most practical way to enhance soil health, and soil health is something you hear a lot about these days, is to promote better management of soil organic matter or carbon. In short, we should go beyond tolerable soil loss and manage for carbon. So NRCS is right on board with this concept, and for obviously good reasons. Now, how long does it take to build a carbon-rich, healthy soil? Not very long if we put our minds to it. So here we have an example from a vegetable grower on the Mendocino coast. The farm's name is Fortunate Farm. She began with the soil you see in the upper left. And 3 years later, this mineral soil was at about 1.5% organic matter. 3 years later, she had 6% organic matter in her soils. And you can see this dramatic difference. It's exactly the same mineral soil. Over a period of three to 4 years, she built her soil up to 6%. Now, that involved using a lot of compost. And so it's not hard to build soil organic matter when you're adding compost, because you can just keep adding compost. And if it's good, stable, finished compost, you can add a lot of compost and build your soil organic matter very, very quickly. She also adopted cover cropping, and she also stopped tilling her soils. So she not only was adding carbon, but she was also conserving the carbon she had by avoiding tillage and by adding cover crops to her system. So carbon farming, this idea of managing the flow of solar energy in the form of carbon through the farm system, allows us to start to begin to think about a climate beneficial agriculture, not just for California, but globally. And doing this allows us to enhance the capacity of agriculture to not only adapt to climate change, but also to mitigate climate change and to reduce agriculture's vulnerability to climate change while increasing farm resilience, but also increasing farm productivity. Now, in one sense, I think it's important that we recognize that all farming is carbon farming, because you cannot farm except by drawing carbon dioxide from the atmosphere to produce your crops. So in that sense, all farming is carbon farming. But what happens to carbon once it enters the farm system? That's really the question. Carbon from the atmosphere ends up in one of three pools on the farm, either in the harvested portion of the crop, which we then send off the farm, in the soil as soil organic matter, or in standing carbon stocks on the farm, such as trees, perennials, windbreaks, shelter belts, riparian vegetation, and so on. How we manage that carbon that we have captured through the photosynthetic process determines how much carbon we end up storing on farm and how long that carbon remains on farm. Measuring that, the impacts of our various farming practices has been made possible largely through the publication of this work by the USDA in 2014, which, as you can see, is titled Quantifying Greenhouse Gas Fluxes in Agriculture and Forestry. So the movement of carbon, methane, nitrous oxide in and out of our farm systems is what is addressed in this document. And it allows us to quantify the benefits of conservation practices on farm. Now, this work underpins this model, the Comet Planner model, which is a very simple to use online tool developed by Colorado State University in collaboration with the Marin Carbon Project, and is now being used by the state of California and by the federal USDA to quantify on-farm conservation practices and their greenhouse gas benefits or impacts, not always beneficial. Comet Planner grew out of a tool called Comet Farm, which was developed at Colorado State University. And when we wrote our first carbon farm plans in Marin County back in 2013, we approached Colorado State University for assistance in quantifying the benefits, the greenhouse gas benefits of our carbon farm practices. And they helped us use Comet Farm, which is a pretty complicated tool to use to get that data from our various farm operations. What we realized in using Comet Farm was the model, first of all, didn't work very well for our Marin grass-based agricultural operations, because it was really developed for Midwestern commodity crops, corn, soybeans, etc. But we also needed to make some assumptions, baseline assumptions, that we felt were untenable. We did not have the information that the model required us to input in terms of baseline conditions. And so we explained all this to the Colorado State folks. And so working with us, they developed this Comet Planner tool, which takes about 35 NRCS conservation practices and quantifies their benefits at the county level. In other words, each county in the country has a soil survey associated with it, and that soil data underlies the information that comes out of the Comet Planner model. So with this tool, we can actually develop carbon farm plans, and we've done so across much of the state, and we're now working with other states across the country as well. With this concept of building a climate beneficial agriculture by being able to quantify the greenhouse gas impacts of our farming practices. This is an image from a sheep ranch up in northeastern California. And you can see one of the first things we did on that farm as part of their carbon farming efforts was to begin an on-farm compost operation, just taking the organic materials that were already on the farm that were just being ignored and left around the field edges, and just not even utilized, simply the so-called waste products of the farm. We were able to begin some pretty significant compost efforts on that farm. We then developed a whole farm plan, a carbon farm plan, which is shown here, or I should say the summary table is shown here. This, what you see here is the practices that were identified as suitable for implementation on this farm, from compost applications to shelter belt establishments to restoration and riparian areas, prescribed grazing, avoiding tillage on their croplands, planting a silvopasture, improvements in their irrigation system. All of these things have a greenhouse gas signature associated with them, a greenhouse gas benefit in this case, again, derived from the Comet Planner tool. And over a single year, once these are implemented, we could expect to sequester about 4,000 tons of carbon dioxide on this 4,500 acre ranch. So a little less than a ton per acre, which doesn't sound like a lot, but as you can see, it adds up when you're talking about large acreage. Over a 20-year period, assuming these practices are all maintained for 20 years, we're looking at over 100,000 metric tons of carbon dioxide sequestered on the ranch, which means benefiting the ranch. The ranch is gaining benefits from all these practices, ecological and production benefits, and the atmosphere is benefiting because we've removed this amount of CO2 from the atmosphere. We then asked the question, well, how much are they emitting with their sheep production and their wool production, right? And can we compare that with the benefits of their carbon farm plan? And so we turned to the literature, and we found a full life cycle assessment on wool production, this paper by Wiedemann and others in 2015. And we compared the emissions of wool production with the sequestration impacts of the carbon farm plan. And the plan, if implemented, would offset 6 to 10 times the greenhouse gas emissions associated with the ranch's wool production every year, which allows us to begin to think about climate beneficial wool production or climate beneficial agriculture. So we think it's a very robust framework and an exciting one to think about what the possibilities are when we think about agriculture across not just California, but really the world. What this enabled the producer to do was to go to North Face and say, hey, this is what we're doing. We're making a serious effort to produce a climate beneficial wool on our ranch. And these are the practices we're implementing. And North Face said, yeah, we like that. And they, in fact, provided the funding that was needed to develop that compost operation that you saw earlier. So this relationship between climate beneficial products and agriculture and the potential for the producer to be compensated at a level that then enables this work to go on farm is a really, I think, an emerging opportunity here. And some of you are probably familiar with the work of Rebecca Burgess and the Fiber Shed in Marin County. And this is really fundamentally her work in collaboration with the Carbon Cycle Institute, developing this effort up in the northern part of the state. And this is a quote from the producer, which was really enlightening for me, because she says, I like to think of carbon farming and the climate beneficial work we're doing now as a change of thought. So instead of doing things normally, obviously we're raising sheep the same way it's been done for hundreds of years, we also think about the soil and the land when we're making decisions. And when I saw this quote from Lonnie, I realized, we thought we were developing carbon farm plans, but the fact is what we're really doing is we're developing carbon farmers. And it's this understanding within the farmer themselves, this understanding of their relationship to the global carbon cycle and the opportunity it presents to their production system. That's really the win here for us. So it's really exciting to see this work expanding across California. Locally, we have several carbon farmers in Marin County. A couple of examples here are Stemple Creek Ranch and Jensen Ranch, who are both working with Cayuchi to provide climate beneficial wool to some of their line of products. So really kind of exciting trends here. This is Organic Valley, has developed a whole PR scenario based around the fact that they are now implementing carbon farm planning on their dairies, not just in California, but elsewhere across the country. We just did a training in Wisconsin last year that involved a lot of Organic Valley folk. And Organic Valley is developing an insetting process whereby they are paying their producers to sequester carbon to offset Organic Valley's own production carbon footprint associated with their milk and product dairy product production. So really exciting opportunities and changes happening in the agricultural sector around this issue. These are just a few examples of carbon farmers in our region, both in Sonoma and Marin County. Of course, Strauss Dairy has been doing this work for a long time. McClellan Dairy, Stornetta, another dairy up on the Mendocino coast, Stemple Creek Ranch, of course. Malt's been doing a lot of good work with carbon farming around their stewardship program across Marin. Of course, the Marin RCD has been a pivotal partner in all of this work. And the other RCDs are coming online as well. We're working now with 42 resource conservation districts across California. And the conservation district framework exists in every state of the union. So the opportunity is really quite significant. The NRCS is climbing on board. They recently approved at the national level a guidance, they call it, for a greenhouse gas mitigation plan, on-farm carbon sequestration greenhouse gas mitigation plan. As was mentioned at the beginning of this talk, NRCS has just provided almost $3 billion for climate smart commodity grants across the United States, 2 of which are being implemented in this region. The Carbon Cycle Institute is partnering on 2, one with Marin and Sonoma County, and one with NCAT, the National Center for Appropriate Technology, which will involve California and several other states in developing carbon farm plans across multiple farming systems across the country. So we're looking at trying to develop a local recognition of carbon farming efforts so that consumers can directly, vote with their dollars, if you will, to support carbon farming efforts locally. It's really important, and I touched on this earlier, to understand that the hydrological impacts of increasing soil organic matter are really significant. And this is recent work revealing that the loss of soil organic carbon in the American Southwest is equivalent to the hydrological impacts of climate change itself. So in other words, we have doubled our drought impacts because of all the organic carbon we have lost. So of course, the good news there is that if we can restore that organic carbon, we can mitigate to some degree the impacts of drought in the American Southwest. As modeled here, a 30% reduction in soil organic carbon, which is at the low end of what we've actually seen nationally, results in a soil moisture loss that is on par with the recent 20-year drought dry climate anomalies in the American Southwest. So there's a very important role here for organic matter, soil organic matter, in the drought resilience equation, and something the state, I think, has yet to really sign on to or understand, frankly. We saw this in our experimental plots in the Marin Carbon Project. You can see that the red is the compost treated plots, and the volumetric soil moisture on the treated plots was higher than the control plots across this particular 2-year period. Now, NRCS has a very simple little formula, which is not particularly accurate, but it's very handy to use, and we use it a lot, which is to say that for every 1% increase in soil organic matter, we can store an additional 25,000 gallons of water. I've adjusted this slightly to say for every 1% increase in organic matter, we get a 1 acre-inch increase in water holding capacity. Because an acre-inch is about 26,000 gallons of water. And it's just easy to remember 1% organic matter is equivalent to 1 acre-inch of additional water on every acre of ground. With this formula, this very simple formula, we can then estimate the water benefits of implementing a carbon farm plan. And this again is that Northeastern sheep ranch, where we look at various practices that impact soil organic matter. Some practices don't, of course. We don't count the above ground carbon associated with windbreak or shelter belt, but we do count the below ground component of that. So looking at just the below ground carbon benefits of implementing these practices, and the 20-year impacts in terms of increased soil organic matter over a 20-year period, because it takes time to build soil organic matter. You're not going to get these water benefits in the first year, but by the 20th year, you should be seeing those real significant increases. In this case, 64,000 metric tons of increased soil organic matter, assuming all of these practices are implemented and maintained for 20 years. We get a net increase of 521 acre feet of additional water storage on that 4,500 acre ranch. Now that's about an inch per acre of additional water, which on a per acre basis doesn't sound like a whole heck of a lot, but when you add it up across 4,500 acres, that's a lot of water. We did this for a Santa Barbara property, an 8,000 acre ranch, and the net effect was 900 acre feet of water. And that's on a ranch that only has 75 acre feet of above ground storage capacity in its reservoir. So we basically a 10-fold increase in storage capacity on that ranch. But looking at the soil, recognizing the soil as a primary water reservoir, which again, the state of California has yet to recognize. So we asked the Flints, Lorraine and Alan Flint of USGS, what it would mean for the state of California if we were to increase our soil organic matter across our working lands by 1%, 2%, 3%. And that's what this data shows here. As you can see, the counties are lined up across the bottom of the graph here. And the impacts on recharge, on actual evapotranspiration, which is to say plant growth, and soil moisture, you can see there is a benefit in every county in the state, some much more so than others. But nevertheless, when we look at soil moisture storage, it's pretty significant all the way across the state. And recharge, groundwater recharge, is also significantly impacted in many areas of the state. So the potential of increasing soil moisture storage and groundwater recharge and plant growth through enhanced soil organic matter across California is very significant, adding up to about 6 million acre feet of hydrologic benefit overall. Now, the state is prepared to spend at least $5 billion to build 1.5 million acre feet of additional water storage capacity in the proposed new sites reservoir. And I'm not saying we shouldn't build that, but we could do much better if we would focus on building the water holding capacity of our soils. So the opportunity is here. The state, I don't think, has quite woken up to the opportunity, but I think the Healthy Soils Initiative with CDFA is a glimmer of hope in terms of recognizing the real potential, not just from a greenhouse gas perspective, but from a hydrological perspective, to build soil organic matter across the state. In Marin County, let's see if I can get rid of this darn thing. Yeah, there we go. A 1% increase in soil organic carbon on all 160,000 acres of Marin rangeland would represent 2.6 million metric tons of carbon dioxide removed from the atmosphere. And it would increase our soil water holding capacity by 26,000 acre feet, which is more water than is held in Nicasio Reservoir. So these are not inconsequential figures, obviously very significant. And given the state of our soils, our rangeland soils in Marin County, and the state of our drought, and on, the opportunity here is really enormous. So NRCS asked this simple question: when the rain comes, is your soil ready? And I think our recent storms have demonstrated that no, our soils are not ready. We're seeing muddy water in all our creeks. We're seeing mud and water running across our roads, erosion everywhere. So we have a long way to go to get our soils into the condition that they could be in. And in rebuilding our soils, we can begin to recharge our aquifers and our springs, and clean up our creeks and achieve all these benefits we're all interested in achieving. So I'm going to turn now to compost. So maybe I should stop for just a second and see if there are any new questions.
Okay. Let's see. Well, here we go with compost. So I'll save that one. And let's see if I can get in again. I seem to be having problems with mine. If you, Lucy, would you unmute yourself and ask your question? Because I'm having a little bit of a problem accessing my comments and questions. Okay, got it taken care of. Go ahead, Serena. I've got your question up. What is the optimal percentage of organic matter in healthy soil? Doesn't it vary greatly depending on the ecosystem, e.g. grassland versus marshland.
Yeah, absolutely. Absolutely. That's why the concept of healthy soil is a dubious one, because a soil is healthy. It's a purely it's a human concept, healthy soil. And the question is, what is that soil going to be used for? What is its use? What is its preferred state? So soil health varies obviously with, as you say, with the ecosystem and with the use of that soil. NRCS has put forward 5% organic matter as an indicator of a healthy soil, but they're talking about a productive agricultural soil. Whereas, a rangeland soil in Marin County, I think if, a 3% level would be marvelous, great to see. So definitely varies with the soil type, land use type, lots of factors to consider there. Yeah.
And do you want me to save this compost question till the end of your presentation?
Well, yeah, let's get into compost a little bit and then maybe take that question.
Okay.
All right. So I thought it'd be helpful to start maybe with the definition of compost. I think many of us think of compost as a soil amendment that has some soil fertility and soil quality enhancing characteristics. The National Organic Program of the USDA defines compost as the product of a managed process through which microorganisms break down plant and animal materials into more available forms suitable for application to the soil. And I've crossed out more available and I've added beneficial because it's not always more available. In fact, one of the benefits of compost is that it can render soluble nutrients less available, which means they're not going to be leached out of the soil as easily as a mineral fertilizer would be. And it's important, I think, that when we talk about applying compost to soil, it needs to be beneficial. That otherwise there's no point in using it. This is maybe my ideal definition of compost in one sense. It's the end product of a managed aerobic thermophilic organic matter decomposition process suitable for beneficial application to the soil. So it's critical that we manage the composting process. Compost absolutely happens on its own. We don't necessarily need to manage it. But when we're talking about commercial composts and in the regulatory framework and so forth, we really need to be managing these piles. They need to be aerobic. They need to be thermophilic. That is to say, they have to get hot. And obviously we want complete organic matter decomposition. And at the end of the day, that compost has to be suitable for beneficial application to soil. So we bring our organic materials together. We make sure they have adequate water. We assemble them into some kind of a unified body we call the compost pile. We make sure that there's oxygen getting to that pile. And then we begin to see heat generated and lost from the pile. Carbon dioxide, of course, is lost because this is a living organism, if you will. It's an ecosystem. It's breathing. It's exhaling carbon dioxide, inhaling oxygen. It's evaporating water vapor. And at the end of the process, it's stabilized. It becomes what we call finished compost. Most importantly, in the context of my thinking, and certainly in the context of this presentation, compost is a source of energy, solar energy, or carbon for the soil ecosystem. It's energy, solar energy, that drives soil-plant water relations and underlies a whole suite of ecosystem processes, including nutrient cycling, biodiversity, hydrological processes, and so forth. So composting is fundamentally a process linking humanity directly and proactively to global cycles and processes. So composting for me is really an opportunity to dance with nature, if you will, to engage directly with fundamental geophysical processes that we can engage with at the garden scale, the farm scale, the landscape scale, the state scale, at whatever scale we want to engage. But this is an entryway. Compost is an entryway into that, building that relationship. This is an image from West Marine Compost, an early spring morning. you can see all the water vapor coming off of those, even though those windrows are covered against the rain. There's a beautiful, clear, sunny day, and there's a lot of water coming off. The raw materials you see on the left are just mounded up, and then the windrows themselves. And of course, there's lots of CO2 coming off there that you can't see, but I assure you it's coming off. Again, these are breathing, living systems, and probably could be a little bit of methane and nitrous oxide coming off of there too, but probably not very much. This is an experimental windrow. Dr. Silver's lab conducted greenhouse gas emission analyses on compost at West Marin Compost. You can see these wooden towers are holding extremely sophisticated instruments. They're actually measuring. They're not in position here because they were just moved out of the way to allow this pile to be turned. But these are stationed around the windrow, and they're picking up, they're reading the greenhouse gases coming off of that windrow. And Dr. Silver's lab found virtually no nitrous oxide coming off of this. This is a food waste compost windrow. There's about 25% food waste here. The idea was to look at manure compost and food waste compost and compare their greenhouse gas emissions. Very little nitrous oxide coming off, methane coming off, but only when the pile is being turned, when anaerobic areas within the pile are exposed and that methane can escape. And otherwise, very little in the way of greenhouse gases coming off of that pile. This data is going to be published, I think, this spring, and so we'll have much more detailed information at that point. A couple of slides from Sally Brown's work. Sally Brown is a compost expert out of Washington State University. She looked at how compost application affects soil quality on farms. She looked at, in this case, water holding capacity, carbon content, and soil bulk density. You can see that as we increase the compost application rate from 20 tons to 200 tons, we see a very significant increase in carbon, of course. We see a decline in the bulk density, that is the weight per volume of soil. And the water holding capacity is interesting because it increases at up to 75 tons per acre, but then it decreases again and again goes back up at 200. So I'm at a loss to interpret that particular data, although I could speculate on what's going on there. But overall, you can see that more compost generally means improved, what we would consider improved soil conditions. In this case, we're looking at what happens to water infiltration rates with an increase in compost. And in this case, the addition of compost results in a very significant reduction in the amount of time it takes for rainfall, or in this case, applied water, to infiltrate into the soil. So again, this has real implications for groundwater recharge and soil water holding capacity and runoff and erosion. This is an example of exactly that from Australia. On the right, we see a bare field, a fallow field. On the left, we see a field that has got permanent pasture vegetation on it, and the identical soils, but you can see without carbon, without organic carbon in that soil, the rainfall has puddled on that soil. It's entrained sediment, so you see a lot of soil carried in that water, and that could potentially be carried off-site. So what we have here on the right is the opportunity to create a downward spiral of soil degradation as we lose organic matter, we lose the ability to absorb rainfall, we lose the capacity to produce growing vegetation, which means we're losing more soil carbon, and we could even have soil running off that site. So over time, managed this way, we can expect that soil to decline in quality. Whereas on the left, we've absorbed all the rainfall, we've got permanent soil cover, we're building soil carbon, we're increasing the capacity of that soil to absorb water and to produce crops over time. So kind of a stark example of two very different ways of managing exactly the same soil with very different outcomes. Now, these are compost application rates which are funded by CDFA. And I'm very grateful for the CDFA Healthy Soils Program and for their compost application subsidies. But I do question the amount of compost they're funding. I think it's extremely low. And the reason for that is they make some assumptions. Particularly, they assume that producers will continue to use synthetic nitrogen fertilizer on their croplands at the same rate that they were using it before compost was applied. And so they're afraid, CDFA is afraid of adding too much more nitrogen to the soil system by over applying compost. So rather than reducing the synthetic nitrogen, they're minimizing the amount of compost that they're going to subsidize on working lands. This is not a regulatory matter. It's not a question of this is all you can apply, but this is all they will support you in applying. The Air Board has assigned a greenhouse gas benefit to this. So if we apply a compost with a carbon nitrogen ratio greater than 11 at the rate of 6 tons per acre, we can expect to see this greenhouse gas benefit. So about 4 tons of greenhouse gas benefit associated with a 6-ton application of compost. Now that's high, but I would say that's a reasonable guess. And you would have to read ARB's entire methodology to understand exactly where these numbers come from. And it's a reasonably interesting read if you're interested in that sort of thing. But just to summarize here that 6 tons of compost applied, 4 tons per acre of greenhouse gas benefit. And this is on an ongoing annual basis. So every time you apply that 6 tons of compost, the Air Board is telling you you're going to benefit about 4 to 4.5 tons of greenhouse gas sequestered on site. Now, this relationship between carbon and nitrogen is really pivotal in the compost environment, and so you will see when you read on information on making compost, you'll see this very typically recommended carbon nitrogen ratio for your starting material for your feedstocks of somewhere between 25 to 1 to 40 to 1. That's 25 parts of carbon to 1 part of nitrogen, up to about 40 parts of carbon to 1 part of nitrogen. Now you can make compost at lower CN ratios and higher CN ratios, but these are more or less ideal. You'll get the thermophilic temperatures that you're looking for, typically with this carbon nitrogen ratio. Now, by the time the compost is finished, because you've been losing CO2 through the metabolic process of the compost pile, you're going to see a decline in your carbon content, which means your finished carbon nitrogen ratio is going to be somewhere between 10, which is very low and unusually low, all the way up to maybe 25, which is a little high. So you can see that your carbon is being lost through the compost process. Ideally, your nitrogen is being conserved. And I like this image because I think of carbon as being the larger wheel and the nitrogen being the little wheel. And within that, within the compost environment, what's happening is the microbes within the compost environment are using carbon as their energy source and nitrogen as their protein source. And they are exhaling, they are respiring carbon. So we're losing CO2, which is why the pile shrinks over time, of course. But if everything is going right, they're recycling the nitrogen. The protein, they're consuming each other, they're eating each other, they're using the protein to build their protoplasm, then they're being consumed by other organisms. And that nitrogen just keeps cycling within the pile. Now, if you're smelling ammonia coming off of your compost, it tells you that you're losing nitrogen. But ideally, again, under ideal composting conditions, that nitrogen will be cycled and recycled and conserved within the compost environment. At the same time, the carbon yes, it's being conserved, but it's also being respired. And so about half of the original carbon ends up leaving as carbon dioxide. But again, ideally, the nitrogen is retained. I'm going to diverge a little bit into nitrogen for a bit because generally compost is considered an alternative source of soil fertility. And the alternative to what? Well, an alternative to synthetic forms of nitrogen, potassium, and phosphorus. Nitrogen is typically viewed as the most limiting factor for plant growth. And it's true that when we apply a little bit of nitrogen to our crops, we see them green up and typically grow more vigorously. So it is, in that sense, a limiting factor to plant growth. But when we realize that there's about 100,000 tons of nitrogen sitting over every acre of ground, we have to ask ourselves whether nitrogen is fundamentally a limiting factor in plant growth, or is it simply that we don't have access to the nitrogen that's available? Now, half of the volume of healthy soil is air, and nitrogen makes up 78% of the Earth's atmosphere. So you can imagine there's a lot of nitrogen in air in the soil, but plants can't access that nitrogen in that form. So it needs to be transformed. And as I mentioned earlier, that happens with rhizobium bacteria or actinomycetes on both leguminous and actinorhizal species. There are free-living nitrogen-fixing organisms in the soil that also take nitrogen from the air and transform it into forms that plants can use. Nitrogen results in nitrous oxides being added to the soil in rainfall. But none of this, it adds up to the amount of nitrogen that we're currently adding to our agricultural systems through the synthetic production of nitrogen fertilizers through this process known as Haber-Bosch. Haber being the scientist who figured out a way to draw nitrogen out of the atmosphere and convert it to ammonia, which could then be used as a plant fertilizer. And then Bosch was able to successfully commercialize that process. And all of this happening around 1920. The nitrogen cycle, which is the global natural nitrogen cycle, is again a global cycle like the carbon cycle, but it's driven by the carbon cycle. So you can see it is the uptake of solar energy by the growing plant that fundamentally drives the nitrogen cycle. So the carbon cycle and the nitrogen cycle are intimately associated with each other, as we see in the compost environment as well. And you can see it involves the atmosphere, the soil, plants, animals, but again, industrial fixation of nitrogen from the atmosphere and its transformation into a form that can be applied to the soil as ammonium and then made available to plants is a significant factor both in global warming and in food production on planet Earth at this time. So this is a schematic of the Haber-Bosch process, which involves a lot of heat and a lot of pressure and a whole lot of fossil fuels. Fouchereau and Bellassin published a paper back in 2011. This is a European paper suggesting that for every ton of nitrogen that we spread as fertilizer, we're essentially emitting 15.5 tons of carbon dioxide. 10.5 tons in the field where it's applied and 5 tons during the production of that material. So a very significant contributor to global warming is, in fact, nitrogen fertilizer production. Nitrous oxide emissions, which is largely driven by fertilizer use from soil, account for 47% of total U.S. agricultural emissions. So very significant component of agriculture's emissions are a result of synthetic nitrogen fertilizer use. 32% of nitrous oxide emissions in California come from our agricultural soils and manure, and much of that manure nitrogen originates as synthetic nitrogen. The other percentage of nitrous oxide emissions comes largely from fossil fuel combustion. The dominant driver of the increase in atmospheric nitrous oxide, which I showed a graph of earlier, comes from agriculture. And there's clearly a conflict between the way we're feeding people and stabilizing the global climate. This is a quote from Dr. Tian from a couple of years ago. A lot of numbers here, but I think what I really want to point out is that agriculture is a primary source of nitrous oxide emissions, agricultural soils. You can see 2/3 roughly of US nitrous oxide emissions are coming from agriculture. And it's equivalent to burning just about 500 million barrels of oil or operating 53 coal power plants every year. So this is not a trivial matter at all. Agricultural soil emissions as a percentage of total nitrous oxide emissions for the United States, about 68%. Composting does emit some nitrous oxide, but relative to synthetic nitrogen, it's irrelevant. Synthetic fertilizer is the largest import of nitrogen into California. And so our excess ecosystem nitrogen is driven by our intentional use of nitrogen fertilizers, our intentional anthropogenic forcing of the nitrogen cycle to manufacture and use synthetic fertilizers. 69% of the nitrogen added annually to cropland statewide in California is derived from synthetic nitrogen fixation. And this is from the California Nitrogen Assessment out of UC Davis 2015. Importantly, this to me is really astounding. Reactive nitrogen, equivalent to 71% of the synthetic nitrogen applied to California croplands, ends up in our groundwater every year, accounting for 88% of the nitrogen input to our groundwater. So when I hear someone tell me that we need synthetic nitrogen fertilizer to produce our crops, I look at these numbers and I say, I don't think so. Most of that fertilizer is ending up as a pollutant in the environment. Overall, looking at global use of nitrogen, phosphorus, and potassium fertilizers, you can see this incredibly steep rise over the last few decades, particularly of nitrogen. Really a dramatic, astonishing increase from about 10 million tons in the 1960s to over 100 million tons today. Now, of course, the global population has also more than doubled in that time. And some say it would not be possible to support that population without the use of these fertilizers. I think the data I just showed you maybe would challenge that assumption, but there's clearly a relationship between human population and the amount of fertility that we're consuming. So globally, farmers supply about 150 million tons of nitrogen every year, but only 35% of this is actually used by the crop. Phosphorus, similarly, less than half of the phosphorus supplied ends up actually being used by the growing crop. And then the same source says that many countries do not use enough fertilizer. Their crop yields suffer as a result. And this is bad for farmers and food security and the environment because it means they need to use more land for agriculture. And I ask the question, really? Because I really have to challenge the assumptions underlying this statement. This is a schematic of what are known as planetary boundaries. This was developed by Stockholm University starting a few years ago and updated periodically. The green zone is our safe operating space globally. We have exceeded our safe operating boundaries in a number of arenas. Our use of water for irrigation, climate change clearly, our global extinction rate, land system change, that is things like deforestation. We're outside our planetary boundaries. Chemical pollutants, plastics, Heavy metals, well outside planetary boundaries. Phosphorus, well outside planetary boundaries. Worst of all is nitrogen, completely outside, way outside of the planetary boundary for safe operating. So clearly we have a problem here. Probably most of us are familiar with this phenomenon, which are dead zones, certainly the Gulf of Mexico, the Mississippi River Delta, is well understood. We lose enormous quantities of soil and nutrients from the crop production areas of the American Midwest. That ends up in the Mississippi River Delta and produces anoxic dead zones in the Gulf of Mexico. But this phenomenon is being repeated across river deltas across the world. Serious problem. Any questions up to this point? Okay, I'll continue. I want to talk a little bit about soil structure because it's something we can directly impact as gardeners and farmers. There's a relationship, of course, between soil structure and the air and water content of our soils, and the ability of soils to hold air and to hold water. A healthy soil should be about 50% air. Soil texture is defined by the sand, silt, and clay content of our soils. We can't really change that, although on a garden scale, sometimes we try. We add a lot of sand or maybe even add some clay, but and certainly organic matter. But generally speaking, we can't really change soil texture. That's the soil that we're given. But soil structure can absolutely be changed by management. Cultivation is fundamentally a destructive process, but we often need to cultivate. So the question is, how can we cultivate in a way that is less destructive? Let's do it at the right time. So make sure that your soil moisture is correct. It's not too wet. It's not too dry. It's at that moisture where you're, as you know, when you turn that soil over, it falls apart, but it doesn't smear. It doesn't shatter. It simply falls apart because the moisture is just right. And then what do you do after you cultivate? Do you enhance your organic matter with compost? Do you make sure your soil is growing a cover crop when it's otherwise bare? These are the questions that there are strategies that you can use to repair the damage you've done from cultivating. When we cultivate, we see a flush of new plant growth. As, for example, when we break open the virgin prairie and we see wonderful production of wheat, that's great as long as that stored organic matter lasts. But then 30 years later, you get the Dust Bowl. So we have to think about what we're doing when we cultivate. Clearly, cultivation is not sustainable unless it's supported with the use of appropriate soil conserving and soil forming and repairing strategies. We need to really be aware of what we're doing when we cultivate. Sorry. No lesser person than Thomas Jefferson developed an improved moldboard plow to facilitate the turning of soil. And this very well may have been the very plow that was used to break some of the prairie soils in the American Midwest. But there's no question that the intensification of agricultural production, and particularly cultivation, is a large player in this relationship between intensive tillage and soil carbon loss. So again, talking about negative and positive feedbacks, in this case, we see positive feedbacks driving very negative system changes, right? Where we till the soil, we lose organic matter, the microbial community changes, we see our soil aggregation declining, our soil drainage declines, the soil becomes more compacted. So what do? We till again, and we just keep this downward cycle or spiral of poor soil health and poor soil condition. And that's really the story of much of California agriculture and much of global agriculture, going back literally thousands of years. The result, of course, again, is global soil degradation. And we are, as I mentioned earlier, looking at very significant degradation of the majority of our soils globally. There's an alternative, of course, to this view of agricultural production, and that is to think about fertility as a phenomenon versus fertilizer as something we apply to soil. Think about, how do we build fertility? I like this concept of bootstrapping fertility, where we're going to build fertility in place rather than relying on external inputs. And how do we do that then? How do we build fertility in place? I think we have to think about the farm and the garden as biological sinks. When we have a fertile garden or a fertile farm, we recognize that it is drawing to it birds, insects, spiders, mammals of all sorts, and of course, solar energy and the vast pool of carbon and nitrogen that sits over every acre of ground. If we think about the farm as a system, as an agroecosystem, then we can begin to understand how we could actually use this concept of positive feedbacks to take advantage of this vast pool of carbon and nitrogen in the atmosphere to build fertility where we stand. Forget the bags of fertilizer. Let's think about, how do we make this garden or farm as fertile, as productive, as diverse as we can. And I like this image because it gives a sense of what it's like to stand in a fertile, beautiful garden and experience the atmosphere of a warm, moist, fertile garden system, which is the opportunity really in front of all of us working with land. We also have this enormous pool, this enormous reservoir, if you will, of mineral, which sits under our feet below the soil. So the rock from which soil is made is continually decomposing, and it's particularly decomposing rapidly under a fertile, organic rich soil, because there are organic acids leaching through the soil. There's a lot of biology going on at that rock soil interface, which is decomposing the rock and making those minerals available to the soil. So we can build soil from the bottom up by engaging the decomposition of our regolith, this interface between soil and rock. But we can also build soil from the top down, as we've been discussing, by building soil organic matter. And this is obviously a very rich, organic, rich soil on the left, but also a soil in process of deepening its organic profile. You can see very clearly the organic rich layer, the less organic rich, and then getting down into that regolith, as I mentioned earlier. And this process is an ongoing soil forming process that we can participate in and accelerate if we choose to do so. Critical to all of this is what Alan Chadwick called conservatoire, which is this process of making sure that the carbon we do capture from the atmosphere is retained within the farm or garden system. So how we manage our discards from the garden is critically important. And this is where compost has a vital role to play, because if we just toss those weeds aside, then the water, the nitrogen, and the carbon embedded in that material ultimately volatilizes and returns to the atmosphere. But if we add it to the compost environment, or we even till it in as a green manure, we are able to conserve that material. And so we can begin to build, through that positive feedback process, we can begin to build soil carbon over time. Chadwick said every pip, we have to conserve every pip, every apple seed has to be conserved, because it represents energy, nutrients, and water that were derived from the atmosphere and the soil that can either be recycled and used to build further soil fertility, or we can toss it aside, send it off to the dump, and in the process, of course, diminish the fertility, the productivity, and the sustainability of our farm system. So that's our choice, and it's critical that we understand that. So I took David Wolf's schematic and I reversed the process and said, well, let's think about positive system change driving positive feedbacks, adding some compost, increasing our soil carbon, decreasing our need for tillage, improving our microbial diversity, improving soil aggregation, and increasing our carbon sequestration, improve our drainage and water holding capacity, improve our soil tilth, and so on, and build this upward spiral of increasing soil fertility and soil health. And this is a schematic from Ratan Lal's work. Ratan Lal is a preeminent soil scientist out of Ohio State University, has spent his entire career studying soil carbon and strategies for building soil carbon on farm. And he shows the difference between a decline in resilience and soil quality and environmental quality through what we could call a degenerative agriculture, which is, I'm afraid, how we might define most of the agriculture on the planet today, as opposed to a regenerative agriculture, which is one which ultimately initiates this upward spiral of positive feedbacks, driving the system to a new, higher state of organization and productivity. So when you hear the term regenerative agriculture, and you wonder what the heck does that mean, from my perspective, this is what it means. It means an agriculture which actually engages the system building process of positive feedbacks to drive the system toward a higher level of productivity, a higher level of biodiversity, stability, fertility, etc. Another aspect of, or maybe I should ask for questions there if there's any additional.
There are no questions at this time.
Okay, great. I think folks are probably getting tired. The aerobic thermophilic composting process also reduces risks to water quality because the high temperatures of the thermophilic compost environment destroy pathogens. So we get the compost up to 131 degrees Fahrenheit, and this is required by law for a commercial compost operation, and also required by the National Organic Program if you're using manure in your compost. So you've got to get that pile up to 131 degrees Fahrenheit, and you got to keep it there for at least 3 days. And in that process, you're going to destroy all of these various pathogens. You're also going to kill any seeds or vegetative propagules, with some exceptions, very few exceptions, but there are exceptions. Your decomposition is accelerated. You tend to conserve nutrients through biological fixation in the pile. You're going to reduce your ammonia levels by conserving and recycling nitrogen. You're going to reduce your water-soluble phosphorus because it's going to become biologically bound within the compost environment. And you're going to reduce the biological oxygen demand because all of that decomposition is going to happen in the compost pile, not in the soil or water to which this compost is ultimately put into contact. Pathogens are also killed. Pathogens have been a big issue. They've been in the headlines, as we all know. The spinach issue a few years ago, E. coli showing up in folks' raw salad and killing a couple of people. I mean, this can really happen. And so if you're going to use manure in your compost piles, or if you're going to be growing produce in an environment where you may have pathogens coming onto the farm system, then it's critical, if you're using compost, that you make sure that it goes through this pathogen reduction phase. This is a graph showing the relationship of temperature and oxygen in the compost environment. And this is a forced air compost pile. There's no turning involved, but there is oxygen entering the pile through a air pump, essentially. And you can see the piles assembled day one, very rapid rise in temperatures, up well above 75 degrees Celsius, which is well over 55 degrees is the minimum, 131 degrees Fahrenheit. So you can see we're well over that. And that temperature is sustained. Again, pathogen reduction, temperature sustained all the way to, let's see, this is from 5.9 to 6.2. So it's almost a month of sustained thermophilic temperatures, and then a gradual decline to more or less to ambient temperatures about a month and a half later. In contrast, we see oxygen plummets as decomposition begins, and that's because the critters in the pile are consuming all the available oxygen. So bam, they take all the air out of the room. And then gradually, as the pile begins to cool, we begin to see a slowdown in biological activity, which allows an increase in oxygen. Oxygen begins to accumulate again in the pile until it almost back up to ambient levels by the end of the process. So you can, this illustrates just how dynamic the biology of the compost environment is and its relationship to temperature generation. Temperature is totally a function of biological activity in the pile. So it's the critters, their activity in the pile that's driving these temperatures. But the energy they use, of course, to drive these temperatures is the carbon. This is the fate of pathogens. This happens to be from a pile made with human waste. And this is what happened to the pathogens in that environment. We start off in May 9th. By May 18th or May 23rd, we've basically killed everything. All the pathogens in the pile are gone. So very, very effective strategy for pathogen reduction, composting. Now, California's Healthy Soils Initiative from a few years ago and Senate Bill 1383 are all pointing in the direction of more compost production and more compost use. It's clear that California can't meet its greenhouse gas reduction goals without a soil-focused working lands program. Compost is the simplest and fastest way to beneficially increase soil organic matter on our working lands. Compost pre-processes and stabilizes organic materials for safe and beneficial application to working land soils. And as I noted, reduces pathogens, weeds, and soluble nutrients. SB 1383, Short-Lived Climate Pollution Act, it's also known as, has a goal of reducing organic waste disposal by 50% by 2020, which we did achieve, and 75% by 2025. And the goal is to rescue for human consumption at least 20% of currently disposed surplus food, but also to require the use of compost and mulches by jurisdictions across California. Now, if we look at California as a whole and we ask what would it mean to apply compost on our irrigated lands, which is about 10 million acres of irrigated land in California. I've seen figures as low as 6 million and as high as 12, but around 10 million acres irrigated land. Virtually all of our irrigated land in California could benefit from compost application. If we applied 3 tons to the acre across that 10 million acres, we would essentially draw 27 million metric tons of CO2 out of the atmosphere to do that. At 6 tons, of course, we double that at 54 million metric tons. And at 20 tons to the acre, we're looking at 180 million metric tons of carbon dioxide taken out of the air. And that could theoretically be done on an annual basis. Do we have enough compost in California to do that? No. But we could probably do this 3 tons on that 10 million acres every year in California. We have just about enough compost to do that. And that doesn't include, this CO2e reduction does not include the avoided methane from diversion from landfill or the avoided nitrous oxide emissions from avoided synthetic nitrogen fertilizer use, nor does it consider the increased photosynthetic capture of carbon dioxide from enhanced plant growth resulting from those compost applications. So all we're talking about is the carbon in the compost here. And that is a whole lot of carbon dioxide removed from the atmosphere to do that. As you can see, it would essentially offset at the 20-ton rate. We would completely offset our electrical generation, our commercial and residential greenhouse gas footprint, and our livestock footprint. So lots of potential. And this is, of course, this is all theoretical, but the numbers add up. And it's just a question of whether or not the state wants to put its mind to doing this work. The opportunity here is to essentially reverse our unintentional industrial forcing of atmospheric carbon with the intentional agricultural forcing of our soil carbon and taking this 420 parts per million, or really 510 parts per million, and drawing it down to perhaps what some consider a safe level at 350 parts per million. I hadn't talked about the squiggly nature of this line that you see in the Keeling curve here. But what this is the intra-annual, that is within year, flux of carbon dioxide in the atmosphere that happens independently of our fossil fuel combustion. This line should be horizontal. It should be a horizontal line, but the squigglies would still be here. And that's because every year we see a respiration, if you will, of about 6 parts per million of carbon dioxide released to the atmosphere over the course of the fall and winter, and then a drawdown of carbon dioxide from the atmosphere of about 6 parts per million over the spring and summer months. And this is reflecting the leafing out of our northern hemisphere forests, our northern Pacific phytoplankton, and their photosynthetic process draws down 6 parts per million of CO2 every single year. Now, if we could just lengthen that drawdown just a little bit, just increase our photosynthetic capture just a little bit each year, we could bend this curve. And that's what this work is really all about. So a lot of jurisdictions, I've heard several communities in Marin and Soma and elsewhere really worried about their requirement now under SB 1383 to purchase and utilize compost and mulch. And for Marin County, this is shown here. These are the communities of Marin that are required to purchase compost and mulch to offset their organic waste production and divert organics from landfill. You can see their annual procurement target in tons of organic material. They call it organic waste. It's obviously not going to be wasted. It's going to be used. But tons of organic material for Belvedere, 165 tons, all the way up to the unincorporated West Marin County at 5,000 tons of compost. And folks are just beating their heads against the wall, wondering how they're going to dispose or utilize all this compost. Well, that only adds up to about 40,000 yards of compost a year, which is frankly not a heck of a lot of compost. If we look at our grasslands in Marin County, not our total raised lands, but just our accessible grasslands that we could actually get to with a compost spreader, it's about 60,000 acres. If we just look at the Marin Carbon Project results at the increased photosynthetic capture of carbon resulting from applying compost on those acres, gaining about 1.5 tons of CO2 from the atmosphere every year, we would offset about 86 or 89,000, 90,000 tons of carbon dioxide annually from a one-time application of compost to those 60,000 acres. It would take 100,000 cubic yards of compost annually every 20 years to do that. So what we obviously don't have enough compost to apply to all 60,000 acres, but if we divide this up into 100,000 cubic yard units, so that over the 20 years, we apply about 2 million cubic yards of compost. So we could apply 100,000 cubic yards annually to some percentage of this total acreage. So 40,000 cubic yards in this context doesn't look like a whole heck of a lot of compost. If we continued this effort for 50 years, we would draw down about 4.5 million metric tons of carbon dioxide. We would also increase the water holding capacity of our soils by almost as much water as we can hold in the Nicasio Reservoir. And this doesn't include our 600 or so acres of cropland and vineyard land, which could, on an annual basis, absorb about 12,000 cubic yards of compost. So there's no shortage of opportunity to utilize that 40,000 cubic yards of compost. And I'm sure all of you as gardeners could step up and utilize some of that as well. And just a matter of communicating that with those jurisdictions. The Marin Climate Action Plan for the unincorporated areas of the county recognizes the potential of agriculture in Marin to essentially account for half of the greenhouse gas emission reductions that are sought within the climate action plan. So about 80,000 metric tons of drawdown and mitigation in Marin's agriculture would achieve about half of the target for the unincorporated area of Marin. So very important and significant opportunity within the context of the Marin Climate Action Plan. Other strategies for drawdown beyond compost, because there are many ways to draw down carbon dioxide from the atmosphere. Riparian restoration is a very significant opportunity. You can see the amount of carbon in a restored versus an unrestored riparian system here. The on the left, the restored, on the right, the unrestored. Lots of carbon associated with riparian restoration projects, and associated with that increase in carbon content of these restoration projects. And here's a 30-year photo sequence from Stemple Creek Ranch, starting in 1990 with a highly degraded riparian system to more or less today, where that system has been restored to abundant vegetation cover and is now supporting over 35 species of migratory birds. We see this direct relationship between enhanced photosynthetic capture of solar energy, its transformation into plant biomass, and that expression as enhanced biodiversity in the landscape. So again, a very significant relationship here. Moving beyond neutral, I know I'm running short of time. This is a document that was published by Lawrence Livermore National Laboratory back in 2020. Getting to neutral, options for negative carbon emissions in California. Someone asked earlier about industrial carbon capture strategies. This includes direct air capture and carbon capture and storage technologies. And the Lawrence Livermore National Laboratory, as a group of engineers, not surprisingly, is very excited about the industrial capture opportunities within California. The goal, of course, in this case, they want to take biomass and burn it, generate carbon dioxide, and pump that carbon dioxide below ground into what they're calling permanent storage. And I stick my tongue firmly in my cheek when I see the word permanent in the context of California and our tectonically active geology. But be that as it may, there's something missing from this analysis. And I think it is this, which I've added here on the right, which is to take that biomass, don't burn it, don't turn it into CO2 that has to be permanently buried, but compost it and turn it into soil fertility, which then allows the enhancement of our natural ecosystems. So use that carbon to generate a positive feedback process within our living landscapes and build and rebuild and restore our living systems in California. Don't remove that carbon permanently from the life cycle, but rather utilize it in rebuilding our biodiverse, complex, and fertile ecosystems throughout California. A very different way of thinking about carbon removal and storage is to utilize that carbon and utilize it in the restoration of California's ecology. So this is what the Climate Center thinks about carbon capture and storage and direct air capture. Carbon capture and storage is a technology for reducing carbon emissions at the smokestack before they're released into the atmosphere. Carbon capture and storage has proven over the decades to be ineffective and expensive, with a majority of projects failing. Carbon captured from CCS has been used primarily to further fossil fuel extraction, resulting in increased pollution. Direct air capture technology works to remove carbon directly from the atmosphere. Direct air capture is in its infancy. It's energy intensive, it's expensive, and it's not yet scalable. Now, if these technologies actually mature and become truly carbon negative, I don't think we can rule out their use, because the climate crisis is so serious that any methodology that actually works, I think, should be deployed. But I do not think we should be using carbon capture and storage in conjunction with biomass combustion, because we're robbing ourselves of the carbon we need, as I said, to rebuild our failing ecologies. couple of other movements in Marin County, specifically the Marin Wildfire Prevention Authority and its ecologically sound practices recognize the beneficial utilization of biomass as compost, mulch, lumber, biochar, and firewood. I think generally we should think about atmospheric carbon that is fixed by vegetation in Marin should really stay in Marin. It should be used constructively within Marin County to enhance our soil carbon, to increase our water holding capacity, to increase our fuel moisture, to build our agricultural and natural ecosystems, resilience to fire and drought and extreme rainfall, and of course, reduce the demand for synthetic fertilizers, and generate this sustainable supply of compost and mulch and lumber and other materials. How can we as individuals support carbon farming in Marin? Well, obviously support your local carbon farmers, buy their products, support the Marin RCD as a pivotal player in all of this work. MALT, its land stewardship program, is doing a lot of good work with carbon farm planning and implementation on their farms. Promote carbon cycle literacy. A lot of folks don't understand the carbon cycle. I would say most folks don't. And clearly making and using compost is a critical piece of all of this. Quoting Aldo Leopold again, who recognized that land is not just soil, it's a fountain of energy. And again, solar energy flowing through a circuit of soils, plants, and animals. And I ask rhetorically, are agricultural ecosystems nutrient limited or energy limited fundamentally? My dear friend and former colleague, Susan Engelbry, first of all, builds these beautiful compost piles. I think you can all agree. But also she made this profound statement, which is that soil is placenta. And if we think of soil as placenta, I think our attitude towards soil, how we manage soil and how we think about the carbon cycle can advance exponentially for the better. The good news is that we can meet our greenhouse gas reduction goals if we immediately dramatically reduce our emissions and seriously invest in our soils and working lands as major beneficial sinks for atmospheric carbon. The bad news, and I've been giving this talk or a version of it for a very long time now, I didn't used to have to say this, but we are now out of time. We're up against it, we're up against the wall, and we need to act, and we need to act at scale. I just stumbled on this very moving plaque from Iceland, a letter to the future. Oak is the first Icelandic glacier to lose its status as a glacier. In the next 200 years, all our glaciers are expected to follow the same path. This monument is to acknowledge that we know what is happening and what needs to be done. Only you know if we did it. And this was at 415 parts per million in 2019. We're now at 420 and rising rapidly. So I'll close there, and if there are any.
And you have lots of questions.
Okay. If we have time, I'm happy to take them.
Okay.
Yeah, we're doing fine. I think Cinda's going to come on about 12:15, so you've got 15 minutes or more. So go for it.
Okay. Can organic compost produce enough productivity to compensate for a decrease in artificial fertilizers?
Yeah, the short answer is absolutely. But it can only do so if we actually engage in the kind of positive feedback processes that I've tried to outline here. We have to be very aware of our conservation of resources, and we have to manage our farm systems in ways that sustain and build fertility. So can we do it without changing our farming systems? No, but we can change the way we farm and build our fertility in place and not be reliant on the fertilizer bag. And that's really the challenge that we face.
If you put freshly pulled weeds into cold compost, how do you know it won't take root in the compost?
Well, that's a good question. Again, if you're generating sufficient heat in your compost pile, then you should be able to kill even things like crabgrass. But this is where turning your pile and managing your pile comes into play, because if you're putting something like, you know, crabgrass into a cold compost pile, you'll soon have a pile full of crabgrass. So it really comes down to being aware of the nature of the material you're adding to the compost, the phase of the composting process that you're adding that material to. So if you don't have a hot compost pile, and a lot of folks in their backyards don't have hot compost piles, you need to be more meticulous about your turning and, you know, picking that stuff out. Maybe at the end of the process, you may actually have to pick out some live roots. But getting the pile hot, which means having a minimum of a cubic yard of material to work with, building the pile all at one time is really great for generating heat. If you're just adding a little bit of stuff every day over months, you're not likely to generate heat. So it really comes down to how are you managing that pile.
How do you know the compost pile is hot enough? Is there a way to test the temperature?
Well, you can use a thermometer, or you can just use your hand. You know, lots of times you stick your hand in the compost pile and it's too hot to keep your hand in there. So you can just use your sense of touch, or you can use a thermometer. Both work pretty well.
My compost became really wet from all the rain. Can I add cut up newspaper to try to absorb the moisture, or any other suggestions?
Maybe when you add newspaper, of course, you're adding a very high carbon material. So you might absorb the moisture, but you're going to really upset the carbon nitrogen ratio of your compost. So, you know, if you add the newspaper and you let it sit for another 6 months, you're probably going to be fine. But if you want to use that material soon, what I would do is keep it covered in the face of future rains. And then before you want to use it, you may want to actually open up the pile and spread it out a bit on a good sunny day. You're going to lose some nitrogen that way, unfortunately. But that's one way to dry it out. You can also just go ahead and apply it wet, and maybe just on the surface of the soil where you're going to be using it, and then come back after a few dry days and incorporate it when the soils and the compost itself are a little drier, and you can actually work them with your garden fork.
So at some point, do we need to stop adding to compost so we are sure it has all become hot enough?
Well, yeah. And again, for backyard piles, I'm not personally overly concerned about high temperatures. For one, they're almost impossible to achieve. And two, you know, I know what goes into my compost pile, and I don't put things in there that I think are going to be a health problem for me or a weed problem for me down the road. So what I typically do is, using this image from Susan Engelbre's photos, I use a wire basket like this. It's about 4 feet in diameter and 4 feet high. And I'll just keep adding stuff. I just keep layering until it's full and I really can't add anymore. And then I lift that wire basket off and I move it next door and I start a new pile. And I come back to this one usually about a year later. So a very passive process, not a lot of heat generated, but I'm not worried about that. I know what went in there and I know where it's going, which is onto my vegetable and garden beds. And it's a very easy, simple way to make compost. I don't worry about the temperatures. On the other hand, at West Marin Compost, which is featured here in the middle, by law, we have to achieve those temperatures, and we have much more material to work with, obviously. We have a much higher mass, which makes it very easy to achieve high temperatures very quickly and maintain them through the necessary time frame. But we assemble a pile all at once. We don't add in layers over time. We assemble that pile all at once, and we get those high temperatures very quickly. Now, at a sort of medium scale, when I was farming in Marin, I would build piles that were sort of 9 feet by 12 feet typically, and I would layer those, green, brown manure soil, green, brown manure soil, and it might take a couple of weeks to build that pile. But once it was assembled, it would begin to heat up. and it would stay hot for quite a long time. So there are a lot of different strategies and different ways to go about this, depending on, at what scale are you working?
I have my own question real quick. I noticed in one of your slides that West Marin had bags of compost now, and before they didn't. So are they bagging their compost now?
Well, it's intermittent, but typically, yes, there usually is bag material available.
Okay. Is compost one type of mulch?
Well, you can use compost as a mulch, but a mulch by definition is laid on the surface of the soil. So if you want to use compost as a mulch, that's fine, perfectly fine. It's if you're buying your compost, it's kind of an expensive mulch. But typically we generally incorporate compost in a cultivated situation. But as you saw with the Marin Carbon Project, we can also just apply it to the surface. Now, the Marin Carbon Project conditions, we applied a very thin layer to standing vegetation. We didn't want to bury the vegetation. So, how you use it is sort of site and circumstance specific. I will typically apply, say, 1 inch of compost or 2 inches of compost, depending on what I'm doing. And then I will incorporate it using a garden fork, but just in the very surface layer, just in the aerobic layer of the soil. So that compost becomes kind of part of the very surface layer of the soil, but the soil and the compost are married together, which accelerates the rate at which the nutrients in that compost can become available for the vegetation that I'm trying to produce there. So there are a lot of different approaches to how you might utilize compost, but you can use it as a mulch if you wanted to.
Where does biochar fit in?
Biochar is part of the equation. The challenge with biochar is to make sure that its production is carbon negative, right? Because if we're burning biomass to make biochar, that intuitively doesn't make any sense. But using a pyrolysis process, which is burning in the absence of oxygen, in which we conserve more of the carbon in that char, and then we utilize that char in various ways that can further conserve carbon in our soils or in our composts. Then, and if it's produced from a renewable biomass source, which is critical, obviously, then biochar makes some sense. We obviously don't want to be burning down our forest to make biochar. That doesn't make any sense whatsoever. But if we have a waste product, and there are biochars, for example, that are being made out of lumber mill waste, that's material that might otherwise be going to landfill, for example. If we turn it into char, we lose some carbon, of course, in the combustion process, but we turn the remaining carbon into a form that is highly durable and also provides a lot of other benefits to the soil, assuming a whole bunch of factors about the soil. So that there are a lot of assumptions around biochar that need to be checked before its use makes sense from a climate change perspective. But there's definitely a place for biochar in this conversation.
I remember at one point I read that Marin County had asked us not to put seeds into the green compost bins. Is that no longer current guidance because it seems to contradict seeds being killed by heat?
Yeah, that's a very strange requirement. I didn't know that had ever been on the table, but that strikes me as completely unnecessary. Yeah.
Our garbage company collects green and food waste each garbage pickup. What do they do with all the compost?
You should call them and ask them, because depending on your garbage company, I don't know, but they will certainly tell you. It's a good question.
Mm-hmm. Can you say more about Marin jurisdictions that are having trouble selling or using Marin sanitary home compost products? I sometimes can find it for sale at American Soil and some nurseries, but not always.
Yeah, that's a good question, and I don't really have a good answer for you. I just know that I've been on some calls with various jurisdictions, San Rafael, for example, that really are worried because they have a requirement from the state to purchase and beneficially dispose of mulch and compost, and they don't know how they're going to do that. But I can't really answer your question. Yeah.
If California wanted to implement the compost strategy you indicated on a previous slide, how much would it cost the state?
Well, that's a really good question because it really depends on how we do the math, right? If you think, how much is it costing the state now to address its groundwater pollution issue, for example? So when we talk about the cost to the state, CDFA, Department of Food and Ag, is paying about $35 a dry ton for compost through its Healthy Soils program. And they're advocating applying up to 6 tons per acre. So that's about $200 about $200 worth of compost that they're willing to subsidize per acre. And if we have say 20 million acres of cropland, what's that, $400 million, something like that. Did I do the math right? No, it's more like $4 billion, I think. So that is probably a low ball if we were going to treat all the state soils on an annual basis. But if we think about the cost to the state, one of, for example, building the $5 billion Sykes Reservoir, of cleaning up our groundwater, which no one has even really tried to do yet. And we have 600 square miles of polluted groundwater in the Central Valley of California. The climate costs associated with our degrading soils, and the opportunity cost of not transforming or moving carbon dioxide from the atmosphere to our soils, I think we would very quickly realize that whatever it costs, it's going to be a tiny fraction of what we're actually going to end up paying to address all these other environmental crises. And we can address them all simultaneously through this one simple methodology. So if we're going to do the math, we need to consider all the opportunity costs here and all the associated costs of environmental degradation of not implementing this strategy.
Is it okay to fill a raised bed just with compost?
Short answer, yes, assuming the compost is of a good quality. But there are some real advantages to engaging with your soil in your garden. And I would encourage you to use a mix of your native soil and compost for your raised beds. But sure, if you a good quality compost, you can grow directly in that. If it's mature, then yeah, you should be able to grow directly in that.
What do you use for a brown layer in a 4x4 basket?
Well, this photo, Susan is using dry leaves collected from her neighbors mostly. Straw works well. You can certainly shredded paper can work. Any wood chips actually are not bad as long as they're reasonably finely ground. So really any woody, any dry material, stable manure can be good if it's got a high percentage of shavings and straw. Those sorts of materials.
Do you worry about rat feces in an open pile? I got a rat-proof composter. I got a rat-proof composter because of rats in my nice warm open pile.
Yeah, rats in the city are a problem, of course, and so keeping your compost vermin-free can be a challenge when you're putting food waste out there on a frequent basis. I try to limit the frequency of emptying my compost bucket, so I use a 5-gallon bucket in my kitchen, so I don't apply food every day for my rodent population. And then when I add the material to the compost, I bury it deep in the pile and cover it either with some finished compost or some shavings or other, shredded paper can work. That doesn't necessarily completely eliminate the rat problem. So it is a challenge. Vermin is a real challenge, especially in an urban setting.
How do you practically turn a compost pile contained in a 4-foot wire container? It seems you would have to climb on a ladder, or if you remove the wire, the pile would collapse.
Yeah, the pile doesn't collapse. But I don't turn these piles. That's the real beauty of this system is I just fill the thing. It takes about a year to where I can't add any more to it because it's breaking down all the time, right? So I'm adding and it's breaking down, I'm adding. And then at some point, about a year down the road, I lift that wire off and I start a new pile. And I let that sit for 6 months, another year, whatever, whenever I'm going to need that compost. And then I open up the pile. And by that time, it's only about 2 feet tall. And I use that material. Usually I apply it in the fall of the year. And meanwhile, I'm building my new pile next door to it. So that's my very passive backyard compost approach. Saves a lot of work.
And that's it with the questions. And I just want to thank you for such a great and informative, useful presentation.
I thank you all for the work you're doing and for your attention for 3 whole hours. I appreciate that.
It was very interesting.
Thank you, Jeff.
No, thank you all very much. Take care, all.